When we talk about life beyond Earth, we usually start with a familiar picture. Blue oceans, green plants, a rocky world that could be almost our own. But the universe is far older and far stranger than that, and life, if it exists elsewhere, may not play by our rules at all. We humans are carbon chauvinists. Every living thing we know is built from the same black skeleton of carbon atoms, swimming in water and breathing oxygen, or something like it. It's easy to feel that chemistry is vast, billions of combinations of elements, pressures, and temperatures, any of which might have found its own path to life. It's also easy to forget that we ourselves are not really made mostly of carbon, we're mostly made of water. The majority of atoms in our body are hydrogen and oxygen. Hydrogen makes up about 62% of our atoms, though only about 10% of our mass, while oxygen is about a quarter of our atoms but 65% of our mass. Carbon, by comparison, is just 12% of our atoms and about 18 to 19% of our mass. Less than a fifth. So when we call ourselves carbon-based, it's not about how much carbon we have, it's about its role. Carbon is the framework, the skeleton that binds all the rest together. And that raises an interesting question. What if something else could play that role? What if on some other world, another element was the skeleton of life, or a different solvent than water carried it along? Even here on Earth, life has flirted with other chemistries. Sulfur, phosphorus, boron, and even silicon all play crucial roles in biology, even if they are not its foundation. There's no law of physics that says carbon had to win, only that it did here, but maybe somewhere else. A different chemistry rose to dominance. So today, we are going to explore those other possibilities, not to replace carbon, but to expand our imagination of what life could be. Some of these chemistries we have discussed before, others we'll be revisiting with new ideas and discoveries. Together, they form a tapestry of possible life that might fill the galaxy. Some of you may have noticed this episode runs about as long as one of our compendiums, which I usually release in the winter when folks are in the mood for something longer. But this is not a compendium, it's something a bit different. You can think of it as an expansion of our 2020 non-carbon-based life episode, which touched briefly on many forms of alien chemistry that we've since explored in greater depth. That's still an ongoing project, but I wanted to bring those deeper dives together here, along with a few new segments explaining ideas we have not yet given a full episode. There's also a poll on our community page for which of these topics we should deep dive next. This anthology mixes new material with several more recent episodes on the same theme, so we can explore the full spectrum of alien chemistries in one place, without playlists and with all the sponsor reads and announcements removed. It is chapterized, so feel free to skip over or ahead to any segment you'd like. This is not a best of, as not every episode we've done on the topic, just the ones that fit together as a single, comprehensive piece. And for my new viewers, as a quick heads up, my speech impediment is stronger in a few of the older segments, especially Void Ecology from 2019. What we will explore. We'll begin with a brand new segment on Boron Biochemistry, the chemistry of dry desert worlds, where boron and nitrogen might weave life from heat rather than water. Then we'll revisit our 2023 episode on ammonia-based life, looking at how organisms might swim in cold oceans, where water would freeze solid. Next, we'll turn up the temperature to explore Sulfur Worlds, where biology might breathe acid and feast on volcanoes. From there, we'll move to silicon-based life, perhaps the most famous alternative to carbon, life built of stone rather than flesh. After that, we'll briefly explore Phosphorus Life, a subtle but fascinating variation that could rewrite what we think we know about molecular information. Then, we'll take a step beyond normal chemistry with crystal aliens, a look at how solid-state or crystalline matter might evolve into living structures. We'll follow that with Fluorine Life, the cold-fire chemistry that might thrive on frozen worlds or halogen-rich planets. And semi-finally, we'll close the classic, Void Ecology, our early exploration of life in the vacuum of space, and then Life on Methane Worlds, our most recent look at biochemistry in the outer solar system, and then have some closing thoughts. It is a long journey, from the blazing heat of Sulfur Worlds to the frozen brilliance of fluorine, from living crystals to organisms adrift in the void, but as we will see, life may be far more adaptable and far more creative than we've ever dared to imagine. So, if that sounds interesting, hit the like and subscribe buttons, turn on notifications, grab a drink and some snacks, and let's begin our exploration of strange life forms, the chemistry of alien worlds, starting with our first stop, boron. Boron Biochemistry, the desert alchemists. When we think of life, we often picture it on worlds covered in oceans or ice, flowing fluid environments where molecules can meet, react, and evolve. But what about worlds where there is no water, only heat, dryness, and rock? Could life still find a way there, not in the depths of seas, but in the hearts of deserts? If so, boron might be the key. On Earth, boron is rare. It's the fifth element before carbon, but only makes up a few parts per million of our planet's crust. Yet that tiny amount turns out to be vital, not to sustain life as we know it, but perhaps have made it possible in the first place. You see, boron plays a quiet but profound role in organic chemistry. In prebiotic experiments, simulations of how life might have begun, boron stabilizes one of life's most fragile molecules, ribose, the sugar backbone of RNA. Without boron, ribose breaks apart almost instantly in water. With it, the molecule survives long enough to start binding into the first chains of information. So even here on Earth, some think boron might have been the match that lit the spark. That makes it a tempting candidate for chemistry of life elsewhere, particularly on worlds where water is scarce but heat and reactive gases are plentiful. Because boron doesn't just stabilize sugars, it's a master alchemist. It can bond with nitrogen, carbon, oxygen, or even metals, forming cage-like molecules called boranes and boron nitride. Indeed, we've talked about using that before as a possible alternative to graphene in space elevators. They are unusual compounds. They are energy-dense, often unstable, and incredibly versatile. Boranes, for instance, store huge amounts of chemical energy, so much that some have been tested as rocket fuels. But under the right conditions, that volatility could power metabolism instead of explosions. In our broader discussion, that's a thing to remember. Anything we can use to absorb power or to store power can potentially be a basis for life. One of the reasons for today's anthology is some of the early draft phase of our upcoming episode on plasma-based life forms, which necessarily is rather speculative, and reminded me of our episode contemplating possible higher dimensional alien life, where our keystone thought is the idea that if we can access energy, we can probably make a machine that could run there. And if you can make a machine there, then you can at least contemplate a life form evolving or adapting there. Needless to say, it's hard to have life in the middle of a star, as while energy is plentiful, chemistry breaks down at such temperatures. Yet there is a lot of room in between a stellar furnace and our everyday water-covered world. So let us picture a planet perhaps like early Venus or Mercury, a hot, arid world where daytime temperatures bake the surface above 500 Celsius, and rain, if it exists, comes as vaporized acid rather than water. There are no oceans, but thick atmospheres of nitrogen, carbon dioxide, and traces of boron-bearing gases which swirl through constant storms. On the surface, rocks crack with thermal stress, and tiny crystals glisten in mineral dunes. Here, life would not swim, it would sublimate, living in a boundary between solid and gas, forming colonies that resemble dust, frost, or glowing crusts clinging to rock. Such life might use boron-nitrogen chains, cousins to the carbon-nitrogen backbones of amino acids. In chemistry labs, these are known as borazines or inorganic benzenes, because they mimic the ring structure of aromatic carbon compounds. On a desert world, they could serve the same purpose carbon rings do in ours, flexible yet stable frameworks that build membranes, enzymes, or information chains. A boron-nitrogen world could even evolve its own equivalent to photosynthesis. Instead of using water and carbon dioxide to make sugars, its life might use nitrogen and boron oxides to produce boranes, compounds that release energy when they react back with the atmospheric oxygen or other oxidants. The cycle would be reversed from ours. Life would breathe nitrogen instead of exhaling it, and exhale boron oxides as a waste. In its deserts, patches of colorless dust might shimmer faintly as they exchange gases with the air, not leaves waving in sunlight, but crystalline mats pulsing with heat. And where water is too destructive, other liquids might take its place. Liquid ammonia could dissolve boron compounds efficiently. On hotter worlds, molten salts or liquid sulfur compounds could do the same. Some chemists have even speculated that boron biochemistry might prefer near-dry environments, a paradoxical form of life that thrives only when water is almost gone, because moisture breaks apart the very bonds it relies on. Imagine the inverse of our biosphere. On such a world, life retreats to the deserts, not the oases. The driest regions are the most fertile. It's like Dune. This may even be where life on Earth could have headed had we not arrived. The chemistry of life has altered a bit over the eons, and as our sun slowly heats up, Earth would lose its seas in 1 billion or 2 years. Far ahead in time, but long before the sun consumed us as a red giant. A slow shift to also utilize boron could replace it, much as we once emitted oxygen as a dangerous waste product, and now thrive on it. What would such organisms look like? Perhaps something like coral or lichen, low crystalline growths that expand slowly across mineral surfaces, growing denser over centuries as storms deposit new reactive dust. Their cells might be microscopic clusters of boron nitride lattices, surrounding trapped gases, reacting when lightning strikes or when the night brings cooler temperatures. Metabolism would be slow, deliberate, perhaps measured in days instead of seconds. These would be living stones, chemistry that endures. And the endurance would be their advantage. On Earth, boron compounds are resistant to radiation and extreme temperatures. Boron nitride is used in advanced ceramics, spacecraft shielding, and even as a lubricant in fusion reactors. It remains stable where life as we know it disintegrates. If living systems could form from such materials, they might survive on worlds that orbit close to their stars, or even within the atmospheres of gas giants, feeding on the energy of electric storms. It's a strange thought, life built from the same material as industrial ceramics, running on chemical reactions closer to propellants than food. But nature has a habit of finding stability in chaos. A boron world might host slow, crystalline organisms that never decay, passing information not through DNA but through layers of atomic structure. The genes of such creatures might be arrangements of boron and nitrogen atoms patterned in 3D lattices, copied when crystals fracture and regrow. Evolution would be geological as much as biological, measured in the drift of dunes and the fusion of mineral veins. Could such life ever rise to intelligence? Maybe not in the way we imagine. It might exist in a kind of chemical communion, vast colonies communicating through changes in conductivity or fluorescence. The entire desert could function as a living circuit, a planetary neural net woven of dust and lightning. Intelligence would not sit inside a skull, it would be the landscape. And while that sounds fantastical, it's not impossible. Boron compounds can conduct electricity, catalyze reactions, and form self-assembling nanostructures. If chemistry anywhere is predisposed to blur the line between biology and technology, boron might be it. On such a world, life and machine could be indistinguishable, both made of the same chemical logic, both born from the same mineral womb. Back here on Earth, boron's trace presence may have once guided the origin of life, stabilizing fragile molecules that would otherwise fall apart. Perhaps on other worlds, it took that role much farther, not as a mere helper to carbon, but as the foundation of a biochemistry all its own. So when we look up at arid exoplanets that shimmer like glass in their stars' glare, we shouldn't write them off as dead. Somewhere on one of those desert worlds, life may be stirring, slow, silent, and sparkling. The first alchemist of the galaxy, turning heat into chemistry and dust into life. Next, we'll leave the heat and dryness of boron worlds behind and turn our gaze to something colder, worlds where life might swim not in water, but in ammonia. Ammonia-based lifeforms. We search for life out in the galaxy in what we call the habitable zone, or Goldilocks zone, not too hot, not too cold. But this presumes alien life is carbon-based or needs water. Could we be overlooking worlds running on alternative chemistries? Today we'll be discussing the possibility of life based on ammonia, probably the most popular alternative chemistry for life that gets discussed, except for maybe silicon as a carbon alternative, and not just discussed in fiction but in science circles too, for many decades. Indeed, NASA has given this a lot of serious thought, such as the 2003 article from NASA Ames, Searching for Alien Life Having Unearthly Biochemistry, written by Harry Jones, which we will borrow from today. The topic of if alien life might exist in the cosmos inevitably leads us to wondering how it might be different from it having arisen on strange new worlds unlike our own, and how this should change our methods for seeking it. Right now, we basically seek out life in what we call the Goldilocks zone, not too cold, not too hot, just right. But unlike in the story of Goldilocks and the Three Bears, we're not talking about porridge but water. A world covered in ice or in which the oceans would evaporate away is not a place where we would expect to find complex surface life on. In the absence of surface life, we would not expect a rich ecology powered by sunlight, but life might live deep underground or in the deep ocean even if the surface of a planet was frozen over, and we discussed that option before, most recently in our episode on Hycean planets and ice worlds. However, it still assumes life is based on water, and there are some very good reasons to think that would at least be the norm for the universe, and maybe the only option. We'll be discussing that reasoning for today, and we'll be examining the possibility that ammonia might be an alternative basis for life, and critically, why it might make a suitable alternative to water. I want to emphasize that we're not talking about ammonia here as an alternative to carbon, as in carbon-based life, but rather as an alternative to water, as the solvent that all the chemistry of life is happening in and with. We are carbon-based life forms, but we have a lot more water in us than carbon, and we're discussing ammonia today as an alternative to that water. Carbon may or may not need an alternative in ammonia environments too, of course. You'll hear folks say we are carbon-based and suggest silicon as an alternative, and we discussed that a bit some years back in our non-carbon-based life episode. But it is important to understand that carbon is only the second largest fraction of mass in your body at 18.5%, while oxygen and hydrogen make up 65% and 9.5% respectively. That's by mass, and 93% of the typical human or animal is made up of those three. Indeed, hydrogen, the most common element of the universe, is the most common in our body too, as hydrogen atoms outnumber every other atom in your body combined. It's just that it is mostly as water, which is made of 2 hydrogen and 1 oxygen atom, and while hydrogen only has 1 proton and 1 electron, normally, oxygen normally has 8 protons, 8 neutrons, and 8 electrons, meaning 1 in 3 atoms in water are oxygen, but they make up 89% of the mass. When we start talking about alternative chemistries for life other than our own, it is critical to know how abundant and available elements and molecules made from them are, and not just inside our bodies. Phosphorus, the last of the big 6 elements in terrestrial life at 1% of our mass, is far less abundant than the other big 6, oxygen, carbon, hydrogen, nitrogen, and calcium, but it is around enough to be available for life to harvest and concentrate to the levels they need, and that would work for other rare elements. But where water is concerned, its abundance is critical as a solvent. Essentially, you need something for all the chemicals to dissolve in and interact with each other, and that's the role that water plays. And water plays that role very well. There are tons of solvents out there in nature, but there's a reason why water is called the universal solvent. More things dissolve in water than anything else we know of, at least when it's a liquid, not an ice cube. It's also insanely common, being made of the first and third most abundant elements in the universe, hydrogen and oxygen. Oxygen is a distant third too, far behind hydrogen and helium, making up only about 1% of the mass of the universe, ignoring dark matter, which is why gas giant planets are huge, but rocky ones made of oxygen or icy bodies are relatively small. They are left over after most of the hydrogen and helium fly off into space. Indeed, oxygen is typically the most abundant element on any planet or planetoid not cold enough or massive enough to hold on to hydrogen and helium against forces that strip lighter elements off the planets. When it isn't forced, it's usually a close second on something like iron or silicon. To come up with alternatives for life, we begin by either contemplating different chemistries that might work with water, or we contemplate options that replace water with another solvent, and that's where ammonia comes in as a potential alternative to water. First, it is very common. Most icy bodies we refer to are made of a mix of water ice, but also methane and ammonia. That's not surprising. Methane is 1 carbon and 4 hydrogen atoms, and carbon is the 4th most abundant element, about half as common as oxygen, just under 0.5% of the mass kicking around in space. And in methane, 75% of the mass is carbon, but 80% of the individual atoms are hydrogen. Nitrogen is decently common too, but about 1/10 as common as oxygen and 1/5 as common as carbon. Ammonia, being one nitrogen atom plus 3 hydrogen, is also fairly common. And as we see here, water, methane, and ammonia all represent very basic mixtures of multiple hydrogen atoms, the most abundant kind, with one atom of the more common elements, oxygen, carbon, and nitrogen. So all are abundant, whereas something like mercury, the quicksilver liquid on which rock can float, and which would not boil on all but the hottest planets, is just not very common, and maybe more importantly, would not be the dominant liquid on a planet where water could exist. Indeed, we often have lighter elements turn molten and float on top of mercury on any place where mercury might conceivably be common, but water couldn't exist. But ammonia is very common and is a liquid when water is not, freezing not until reaching -78 Celsius or -108 Fahrenheit. It is also a good solvent, not the equal of water in some respects, but better in other respects, such as being able to dissolve metals. It also has a lower viscosity, making it a better medium for movement of ions. But critically, ammonia is a vastly superior solvent to frozen water, so on colder worlds it's abundant enough to take over that role. Water ice, while likely to be very abundant compared to that ammonia, forms the ground on which a lake of ammonia might exist, as ammonia has a density of 0.73 kilograms per cubic meter, versus 0.9 for water ice and 1 for water. However, water ice is soluble in ammonia, so in that case, the lake might dissolve the underlying ground, and you would end up with a eutectic mixture rather than pure ammonia. Another issue though is that frozen ammonia is denser than liquid ammonia at 0.86, thus ice cubes of it would sink in ammonia, rather than float the way water ice does in a glass of water. No ammonia icebergs on a sea of ammonia, though it is less dense as a liquid or solid than water or water ice are. Life based on water and in water has the advantage that water self-insulates, freezing from the top down, allowing water to exist even when on the other side of that ice, and the temperature may have fallen to fall below freezing, which is handy if you have significant periodic temperature variation on your planet's surface, from daytime and year length. This is potentially a big issue with ammonia lakes. I have heard it discussed as a requirement for life on Earth that ice be less dense than liquid water. Ice, the solid form of water, will float on it, but many solids are denser than the liquid they are frozen out of. Water's properties in this regard also encourage ocean currents, which might be more difficult for ammonia. A workaround might be where ammonia and water both exist. The water might freeze and float and insulate the lower ammonia-rich layers. A very great deal depends not just on the composition of a planet, but its average temperature and how that temperature varies from factors like day or year or latitude or depth. Temperature ranges on planets are not evenly distributed. Most of the bodies in the solar system are far too cold for liquid water to exist on the surface, or often even some underground pocket. It's not a case where planets gain twice as much sunlight have twice as high a temperature. Things in nature tend to reach an equilibrium point on their upper layers where the sunlight coming in gets absorbed and re-radiated as infrared waste heat at an equal rate, and will warm or cool till that equilibrium is reached. But that goes with the fourth power as a first-order approximation. Earth has an average temperature of 288 Kelvin, just 15 Kelvin above water freezing. Ammonia freezes at 195 Kelvin, so a planet on average 15 Kelvin warmer than that would be 210 Kelvin. That is 73% of Earth's average absolute temperature. That would imply it only got 28% as much light as Earth, about what we expect from an object twice as far from the Sun as us. Past Mars, but in from the asteroid belt. Let me emphasize that was on a first-order approximation, and other energy sources like leftover heat of formation, radioactive decay in the core, and tidal heating have way bigger effects proportionally on keeping that planet warm as sunlight diminishes. What it basically means though is that a planet like Earth could have seas of liquid ammonia while still being close enough to its sun for us to imagine photosynthesis or some other solar-powered pump for life operating and permitting a robust ecology. Ammonia is also a good heat reservoir, even better than water, making it slower to rise or fall in temperature. Clouds of ammonia and ice of ammonia are both white, like water, making them more reflective to incoming light. I suppose strictly speaking that the ultimate medium for stable life temperatures would be very reflective when as hot as cloud vapor and opaque and absorptive as an ice. Atmosphere on a world of ammonia seas, even colder ones, would have a fairly high percentage of ammonia vapor, as an analogy to water vapor and humidity, as ammonia has a high vapor pressure, though that can be a downside too. The hydrogen bonds in water are stronger than ammonia, and that affects not just vapor pressure, but also surface tension of a liquid and how hydrophobic or hydrophilic other chemicals are to it, the ammonia equivalent of that. There are doubts as to if very simple early life could hold itself together well enough to allow a self-reproducing system. Titan, Saturn's biggest moon and with an atmosphere thicker than Earth's, might be a good place to get a look at what chemistry goes on in ammonia-rich environments, and speculation that Titan might hold life is often assuming ammonia-based chemistry. Using Titan as an example, there is a decent chance that these worlds would have thicker atmospheres on account of being colder and farther from their suns, even if much closer than Titan, which might help protect the ammonia from UV, and it's possible that photochemistry could produce a high-altitude haze analogous in function to ozone, but these worlds would still fare better around lower UV stars, which conveniently are the majority of them. Our Sun is one of the biggest and hottest 5% of stars, and thus releases a larger share of its light in the blue, violet, and ultraviolets than cooler stars do, which are stronger in oranges, reds, and infrareds. It is harder to speculate on colors. By default, we would expect the same blue skies as Earth gets, with the same reddening at dusk and dawn, perhaps slightly more reddish if there is indeed a protective high-altitude haze. Ammonia is a better solvent for alkaline earth metals, which might become the equivalent of salt in their equivalent of saltwater oceans, so you might get seas of ammonia with a gold or bronze shade to reflect those alkalines while fresh ammonia remains blue. Nitrogen is plentiful in Earth's atmosphere and would be expected to be on an ammonia-heavy world too. It is harder to make the case for free oxygen in the air since ammonia is flammable in oxygen, though nitrous oxide ought to be plentiful enough. As a caveat though, ammonia is not super flammable like gasoline, which will burn when it's at a concentration of just a couple percent in the air, but in the 15 to 28% range, more like carbon monoxide. Alternatively, water vapor is only a few percent normally too, so ammonia at that concentration as a substitute for water would not be flammable. That is all dependent on overall pressure and ratio of oxygen in that air too. Still, I wouldn't be too optimistic about ammonia and oxygen both being in larger concentration in an atmosphere, but we probably don't want to casually rule it out either. Additionally, it may be that life on terrestrial planets based strictly on ammonia rather than ammonia water solution would be more likely on so-called carbon planets. These worlds are speculated to form around stars favoring carbon over oxygen to the point that rocky worlds are based on carbides rather than silicates. Such worlds could have seas of ammonia without necessarily also having lots of water ice around. Early worlds would likely have lots of various hydrocarbons around though. We think a case can be made that vegetation on these worlds might be dark or black as opposed to green. Unlike water worlds like Earth, plants on ammonia worlds may not need to deprotonate water or ammonia molecules to get an electron for photosynthesis. This is because the dissolved alkaline earth metals release solvated electrons that can be used directly. This could free up photosynthetic plants to use a wider range of the spectrum. Nonetheless, we're not really expecting dense life like we see in rainforests. Many alternatives to water have been proposed, but ammonia has remained the strongest candidate since J.B.S. Haldane first suggested at a symposium back in 1954. One of his strongest points is that a lot of water-related organic compounds have ammonia-related analogs. These could serve as a basis for life. One objection to ammonia, and there are plenty, is that it has a lower range of liquidity. Water has a 100 degrees Celsius or Kelvin or 180 degrees Fahrenheit range of being water at normal pressure. It's a good deal higher at higher pressures, while ammonia's range is smaller, only about 44 degrees Celsius or 80 Fahrenheit. It boils at a mere negative 33 Celsius or negative 28 Fahrenheit, and freezes at not much less, and if you're wondering, the ammonia you use at home is usually mostly water. Ammonia mixed into water is a great antifreeze solution. I suppose we might contemplate life based on ammonia-rich water, or which existed in one state in pure ammonia, and as the planet warmed in the summer, an ammonia-rich mixture of water, but in truth I don't see the temperature variation mattering much. Water is liquid from 0 to 100 degrees C, but few lifeforms can exploit the upper end of that range. Proteins can be damaged at temperatures significantly below the boiling point of water. That might be less of a problem for ammonia-based lifeforms, In fact, a bigger problem might be molecules being too stable for metabolism at liquid ammonia temperatures. Also, since liquid ammonia does not expand as it freezes the way water does, freezing might not be fatal for ammonia-based organisms as it is for us. Freezing in the wintertime and thawing out again in the spring might simply be part of their life cycle, so the habitable range of temperatures in ammonia might not be much less than it is in water. We also probably do not want to assume the pressure is the same as on Earth. Substances usually have a wider range they are liquid at higher pressures, and lower when the pressure drops, to the point that you can't really have liquids in a vacuum or near vacuum. Temperatures vary less when you're colder. Pluto, for instance, varies from -233 to -223 Celsius, a mere 10-degree difference. And while there probably are higher and lower spots, Pluto is not explored much or in detail, there's just not much room for temperature variation, even though its high eccentricity means it gets 275% more sunlight at perihelion than when it's furthest from the sun, aphelion. There's no liquid ammonia on Pluto's surface, of course. We're talking about worlds considerably warmer for ammonia oceans, even if frigid compared to Earth, but there's definitely ammonia on its surface, and there may be liquid ammonia pockets below the ice. Indeed, Pluto has cryovolcanoes that we think erupt an ammonia water mix onto its surface. As for Ammonia Worlds, their atmospheres are likely to be rich in ammonia and methane, which are greenhouse gases. This may help to further moderate temperature extremes. It may be that some ammonia worlds can remain within ammonia's liquid range even at the poles, especially if air pressure is higher, expanding that range. NASA aims increasingly views ammonia as a biosignature to look for, since it's such a key ingredient in life-based chemistry and so short-lived in the presence of ultraviolet. So finding it on a planetary surface like we have on Pluto strongly implies activities depositing it recently or regularly. Not necessarily life, of course, but it implies active cycles and churning going on below, and where you've got motion and activities in liquids, life becomes a lot more plausible. On the more general topic of searching for plausible alien life locations that are not very Earth-like, and speaking of NASA aims, I mentioned a short article on alternative alien chemistries they did in 2003 near the start of the episode. In that paper and a previous one, 20 basic principles of extraterrestrial ecology, or exoecology, are summarized under 5 general areas, and I'll quote those now. We have 5 categories, each with 4 principles under each of its headings. Those categories are environmental interaction, ecosystem design, ecosystem dynamics, material cycling, and temporal cycles. Let's run through those and then we'll boil it down, both in the case of ammonia and generally, and I'll interrupt the quotation occasionally when it is using a term that might not be obvious to the casual listener. Category A, environmental interaction. A1, the exoenvironment will limit the potential types of exoecology. A2, different exoenvironments will support different ecosystems. A3, the exoecology will be adapted to its environment by evolution. A4, the environment will be affected by any exoecology, which boils down to saying alien ecologies are limited to what alien environments permit, but likely to have some diversity, such as Earth does between poles and tropics, seas and land, and that life there will adapt to those environments, and those environments will be altered by that. Things change when plants arise and change the plant's albedo or reflectivity, alter the atmosphere makeup, and bigger critters like beavers start making dams and so on. This is all important for basic consideration, but also be mindful that when looking for astronomical biosignatures, we may take for granted they will exist, as the planet will be changed by life being on it. Category B, ecosystem design. B1, an ecosystem will require energy input and use material recycling. B2, an exoecosystem will contain a trophic food web of producers, decomposers, and possibly primary and secondary consumers. B3, the number of trophic levels will be 4 or fewer. B4, an exoecosystem will have an hierarchy of compartmentalized subsystems. Or essentially, life needs energy, needs to be good at using it and recycling elements, and that, as a result, it tends to include components that do that recycling, which means eating each other, eating waste, decomposing waste, and so on. Trophic levels are basically the food chain. Level 1 are primary producers like plants. Level 2 would include herbivores that eat those plants, Level 3 are carnivores, Level 4 are apex predators. And we usually talk about food webs these days, as nourishment can flow around in a lot of ways, like we can eat plants, eat critters, eat carnivores, and even eat each other, and we can also feed all of the above. Category C, Ecosystem Dynamics. C1, the energy flux and storage will be an order of magnitude lower for each higher level of the trophic pyramid. C2, higher energy flows between trophic levels will increase stored energy and ecosystem diversity. C3, energy will be dissipated and converted to heat. C4, energy is not necessarily the limiting factor in exo-ecosystem growth. How much energy a world is getting is a big factor in how big and complex these situations can be, and an ammonia-based world is likely to be on the lower end of that, though again you might have a photosynthesis analog on a colder world orbiting a dimmer star low in ultraviolet, but we're often assuming alternative cold chemistries like ammonia, or methane for that matter, are running on far weaker overall energy supplies, especially given that we often imagine them on smaller worlds like comets or icy moons. Or more of the SFIA K2 Dyson swarm style of conversation, larger megastructures with vast amounts of engineering at every level including genetic might be able to get away with more trophic levels. Obviously such megastructures are themselves signs of life of some sort. Category D, Material Cycling. D1, the material cycle will be closed by decomposers. D2, material cycles with a gaseous phase will cause uniform distribution of the material. D3, materials with no gaseous phase will have a more varied spatial distribution of the material. D4, material availability may be a limiting factor in exo-ecosystem growth. All life eventually needs to be recycled around those basic building blocks again to be reused or life won't last long, and factors for how well it works or how plausible a system is for permitting it need to contemplate what states of matter can be used too. So for instance, life made of big frozen blocks of matter rather than liquids or gases is occurring at a very slow speed. And Category E, Temporal Cycles. E1, temporal cycles in exoecosystems can be caused by external or internal factors. E2, external astronomical factors may cause day and night, tides, and seasons. E3, internal dynamics will cause exoecological succession. E4, stable systems typically have only one limiting factor. And Category E we may boil down to saying that day or night or seasonal cycles are going to have a huge impact on how life operates in that environment and how stably it does so. Stable is good, though of course you also need some change and chaos to disrupt ecosystems if you want them to change, as otherwise critters get hyper-specialized to that niche, which you can argue would tend to limit it getting evolved to really impressive states like technological civilizations. More generally though, a world with constant crazy changes or really complex cycles, like a planet orbiting eccentrically around a pair of binary stars, which also vary themselves a lot in brightness, is not a place we think of as being super friendly for life to begin and dwell. In that same vein, we can look at a planet that's ultra cold and see the presence of liquid helium, and say that might be ultra low in temperature, but superconductors could run there and natural computers might form and thus have brains. But the timeline for anything happening with chemistry in that sheer cold is so immense that we wouldn't expect such life to have had a chance to emerge yet. Maybe long after the stars are born out, or in a different universe with factors just different enough that stars never really formed much or got as hot. And our 5 categories are less of a hard list on where life can or can't be than they are a reminder of what we need to consider when we do come up with an alternative option. Yes, a hot planet might have liquid mercury still, but is that abundant enough and concentrated enough to offer ecosystems? And what's that heat doing to those other categories? Not much complex chemistry with big long protein analogs seems very likely in that level of heat, and of course is utterly impossible inside a star, another place popular to contemplate life in science fiction, but not in astrobiology or exoecology, unless it was running on some exotic matter like matter or magnetic monopoles. And again, we can always find a what if or an exception, but as we run it through those categories, the realism of the situation gets iffier, especially when contemplating natural life as opposed to something we might artificially tailor to such places, which cannot be ruled out of course. Life may never form on a place so cold it has hydrogen and helium oceans, but somebody may have created some, and the word life gets very ambiguous in a technological context too. Such a world might be home to an uploaded digital civilization enjoying the safety and computing efficiency of life under the liquid helium oceans of some rogue planet. But for our purposes today, the key thing is that while ammonia-based life definitely has some factors working against it, it does not break or push any of those categories. It is very abundant, and the worlds on which it might be abundant are also not something we would expect to be hyper-rare or dominated by some alternative like water, except possibly what we might deem an antifreeze planet, where the seas were ammonia-rich water varying in concentration by location and season. This, unfortunately, is the limit of our speculation. We would expect ammonia planets to be less abundant in life than water worlds, and probably an order of magnitude less common too, and likely as a result slower to evolve, so probably not a common chemistry among spacefaring civilizations in the universe. But in a galaxy of trillions of planets, should it turn out that simple life arises fairly often, even if intelligent life is a rarity, that many worlds have algae or slime on them, then I would say there's a good chance a small but not minuscule portion of those might be based on ammonia, and it might have some non-microscopic ecology too, though odds aren't great that a colder, slower world would evolve complex life. Of course, some red or orange dwarf might have had such a world circling it for 10 billion years at this point, so maybe they had enough time. And such stars will live for tens of billions of years to come, too. The good news for them is it might be easier to get galactic colonists to leave those planets be. We often imagine it being hard to quarantine worlds with very primitive life on them, that after you find enough examples of alien algae and bacteria without anything even as complex as an insect on them, you stop trying to keep people from settling them, even if it ruins that local ecology. But a planet so cold it makes Antarctica look toasty probably would not be as high a priority destination for most colonists, even if it didn't stink of ammonia and have an atmosphere that would burn if the oxygen from your habitat leaked out and sparked. So whether or not there's life out there based on ammonia chemistry, it's not likely to be a popular tourist destination for folks from Earth. So that was our look at ammonia-based life back in 2023. Probably the most commonly suggested alternative biochemistry, followed closely by silicon-based life, which we headed to shortly. But before we get there are a few other chemistries we touched on in passing way back in non-carbon-based lifeforms that I haven't yet had a chance to give a full episode of their own. One of those is sulfur-based life, and much as methane-based life is the run-up to ammonia for best cold world chemistry, sulfur sits just under silicon for hot planets, but for different reasons, some of which might work on cold volcanic moons like Jupiter's Io. It probably deserved its own dedicated episode too, but for now, let's spend a few minutes looking at it. Sulfur Worlds, the fiery biochemistries of volcanic planets. When we imagine alien life, we often picture lush worlds with blue oceans or icy moons with buried seas. But sulfur whispers of a different promise, one born not in the gentle chemistry of water, but in the smoke and fire of volcanoes. On Earth, sulfur is already part of life's story. Some of the earliest metabolisms may have run on sulfur chemistry, drawing energy from reactions of hydrogen sulfide long before photosynthesis or oxygen appeared. So unlike most of the chemistries we will discuss today, we already have proof at least one form of this one works. Ironically, we might even be descended from organisms that were partly sulfur-powered, and of course, sulfur still makes about 0.25% of human body mass. In modern times, primitive microbes still thrive in boiling acid pools, feeding on hydrogen sulfide and exhaling elemental sulfur. It's a powerful reminder that this element, so often associated with decay, also fuels rebirth. And we can do that here, on a water world at modest temperatures. Imagine what it could accomplish on planets where sulfur isn't an odd impurity, but the foundation of biology itself. Sulfur is a remarkable element. It sits just below oxygen on the periodic table, and like oxygen, it lives to form bonds. Lots of them. But unlike oxygen, sulfur is promiscuous in its chemistry. It can appear as sulfides, sulfates, polysulfides, and even chains of pure sulfur atoms, flipping easily between oxygen states from -2 up to +6. That flexibility could give alien metabolisms an entire spectrum of energy sources to exploit. Picture a world much like Io, Jupiter's tortured moon, or a super-Earth orbiting close to a dim red dwarf. The surface is streaked in yellow minerals and rivers of molten sulfur. Volcanic lightning crackles through an atmosphere thick with sulfur dioxide and hydrogen sulfide, while beneath the haze, liquid sulfur or sulfuric acid forms dense, reactive seas. It's a chemistry too harsh for water-based life, yet it may be perfect for something born to breathe sulfur. On such a planet, photosynthesis might not mean using sunlight to split water, but using lightning or geothermal energy to drive conversion of sulfide to sulfate, storing chemical energy chains in sulfur atoms. Life might exhale bright yellow vapors instead of oxygen, and cells could be armored in sulfide ceramics rather than lipid membranes. Even vision itself might differ. In this perpetual glow, eyes could evolve to see deep into the infrared, tuned to the heat of volcanic vents rather than daylight. There's even a precedent here on Earth. Deep under the oceans, sulfur-oxidizing bacteria power entire ecosystems without sunlight, and some species already use elemental sulfur granules inside their cells as energy storage, tiny batteries of pure chemistry. Extrapolate that one evolutionary step further, and you could fill a world with creatures powered by the same element that gives us the stench of brimstone. It's easy to dismiss such biochemistries as too extreme, but sulfur reminds us that life's story is written in more than one language. For every blue planet of water and oxygen, there may be a yellow world of fire and sulfur, where evolution dances to a hotter rhythm. And if our telescopes one day catch the spectral fingerprint of sulfur compounds where they shouldn't be stable, perhaps we'll know that somewhere out there, under skies of acid rain and volcanic glow, something alien is breathing out the smoke of life. In the grandeur of the universe, the tapestry of life may be woven from stranger threads than we ever dared to dream, and spun from materials far different to our own, which takes us to silicon. Silicon-based life. In the grandeur of the universe, the tapestry of life may be woven from stranger threads than we ever dared to dream, and spun from materials far different to our own. As we've studied the immensity of the cosmos, we've spent decades searching for life as we know it, clinging to the belief that the universe must be teeming with carbon-based organisms like ourselves. But what if life's building blocks are not limited to the familiar carbon atoms that compose our DNA and proteins? What if, out there among the stars, there exist beings unlike anything we've ever imagined, life forms fashioned from the silicon of alien worlds? Today, we'll embark on a journey of imagination and scientific exploration to ponder the possibilities of silicon-based life forms, creatures that could thrive in environments hostile to our kind and challenge our very understanding of life itself. I am your host, Isaac Arthur, and I hope you'll join me today as we delve into the realms of silicon-based biology, where the chemistry of the cosmos takes on new and exotic forms. This is not our first look at alternative chemistries for life, and when we explored ammonia-based life forms earlier this year, there were many requests that we should look at other chemistries, silicon-based life forms being foremost amongst them. We may cover those others down the road, but silicon turns out to be a big enough topic on its own. So grab a drink and a snack and relax. We'll be here for a bit. And make sure you like and subscribe to the show and hit the notifications bell if you want alerts when new episodes come out. Now, odds are good that you've heard folks mention the possibility of silicon-based life forms before, and for those curious, we are not discussing machine intelligence, AI, and computer brains today, except as a minor tangent. The concept of silicon life predates the discovery of the silicon semiconductor, which is from the mid-1950s, and would not become synonymous with computers or robots for some years. Indeed, sci-fi from that era and earlier focused on calling them ion-based life, or references vacuum tubes, glass and steel constructs, like the skyscrapers that were beginning to dominate skylines of bigger cities. While silicon life forms as a concept was probably popularized by the Horta in Star Trek's 1967 episode, The Devil in the Dark, the idea is much older. Way back 132 years ago, in 1891, German astrophysicist Julius Scheiner suggested that silicon's similarity to carbon might make it an alternative for life out among the stars. And at the time we couldn't distinguish our galaxy from the wider cosmos, and had no idea about the age of the universe, or how elements like carbon or silicon came to be. But if you've seen the periodic table, it's hard to miss silicon there right under carbon and sharing many of its features. Critically, that they are both tetravalent, tetra meaning 4 and referring to the outer layer of electrons of an atom, the valence electron shell, which has 8 openings. So any atom that is tetravalent can have 4 covalent bonds to other atoms. And in the case of carbon, this is how we have methane, composed of 1 carbon atom with 4 hydrogen atoms attached to it. How many covalent bonds an atom can take is important, especially for our big 3 of oxygen, nitrogen, and carbon, which are divalent, trivalent, and tetravalent respectively, or it would have 2, 3, or 4 bonds. Those 3 are also incredibly common, with carbon being a byproduct of helium fusion and a common substance in the universe, while the CNO cycle, or carbon-nitrogen-oxygen cycle, fuses carbon into nitrogen and oxygen, both very common in the universe too, especially oxygen. All 3 have very common partnerships with the most abundant atom, hydrogen, to form oxygen plus 2 hydrogen, water, nitrogen plus 3 hydrogen, ammonia, and carbon plus 4 hydrogen, which again is methane. Those 3 substances are most of what your typical comet is made from, and are what we are usually talking about in space context when we reference volatiles and organic building blocks, and make up a large fraction of the matter in this universe once we remove dark matter and hydrogen and helium. Indeed, it's the largest fraction of atoms made since the Big Bang. Most hydrogen and helium date back to the first couple minutes of the universe. It's no surprise then that something similar to carbon by being tetravalent would interest us as an alternative, and indeed the methane equivalent of silicon exists and is called silane or silicane, and is 1 silicon atom plus 4 hydrogen. There are other tetravalent atoms, germanium for instance, which was our preferred semiconductor material for a time till we switched to silicon, which is better at higher temperatures, and that's where silicon as an alternative to carbon for life starts coming into play, places where carbon chemistry couldn't function for the heat. As we discussed back in our ammonia-based lifeforms episode, what we really mean by carbon-based life and water-based life is chemistry built on carbon but inside water as a solvent, and ammonia is a good solvent too, if not quite the equal of water as a solvent, but freezes at a much lower temperature than water and thus opens the door to life in very cold places. Silicon goes the other way, opening the door to hotter temperatures. And as mentioned, ammonia is an option because nitrogen is quite common in the universe, but there are about 1/3 as many silicon atoms as nitrogen and around 1/10 as much as carbon. More importantly, here on Earth, in our crust, silicon is the second most abundant element, right after carbon, and indeed most of our rock and dirt and minerals are made of those 2 substances. Ironically, silicon's abundance here on Earth, compared to carbon or nitrogen, actually hurts it as a candidate for life, since it is more abundant than both, neither making up even 1% of the matter in our crust, and yet the more abundant silicon is a relative non-factor in the life that did form here. One caveat, it may be that silicon-based life is far more common on planets like Earth, and we just happen to be the freak case where carbon life popped up first, and became dominant and crushed any competitor that formed later. But that seems like a stretch. Still, when you only have one example of something, in this case, life, we should not take for granted that it's the normal situation. Silicon has other things that make it weaker for possible organic or quasi-organic chemistry, and as an example, silicon is much more massive than carbon, more than double, which means it puts a greater strain on molecules it is part of, though it also makes it more temperature resistant since an atom of it jerks around less at the same temperature. Silicon and carbon polymerize differently too. Carbon polymers are frequently long chains of carbon attached to each other, and polyethylene, for instance, is basically a long chain of carbon atoms, where each carbon atom has a bond to 1 carbon on either side of it, and 1 hydrogen on either other side of it, much akin to hydrocarbons we use for fuel, while silicones are made of silicon to oxygen, not silicon to silicon linkage. Carbon forms these large scaffolds of atoms on which other atoms can latch on, and thus is the basis for our organic chemistry and life. This is a major reason why we talk about carbon-based life at all, given that it's not even 1/5 of your body's mass, which is almost 4 times more weight of oxygen and is heavily outnumbered by hydrogen atoms. It is not the only scaffolding non-metal though, nor is it just silicon, Boron and sulfur are other examples, and they too get suggested as an alternative basis for life. Silicon also readily bonds to oxygen to form simple silicon dioxide, most commonly as quartz, and again silicon and oxygen make up most of the ground you're standing on. Silicon dioxide is highly stable and inert compared to carbon dioxide. Silicon dioxide isn't particularly soluble in water either, which is okay as we're mostly interested in hotter places than liquid water would be at, but helps explain why life on Earth is made of carbon, not silicon. No, what we are really thinking of in regard to silicon-based life isn't it arising on Earth-like planets or cold frigid ones where ammonia might be king, but rather on hellishly hot planets like Venus where carbon is actually very abundant in its atmosphere, but where carbon chemistry isn't viable from the viciously hot temperature. Odds are you have a pair of silicone mitts at home for pulling hot objects out of your oven or some silicone utensils for your non-stick cookware, and if not, I'd strongly recommend them. But it is temperature resistant, also solvent resistant too, again making it tricky to couple with water or ammonia as a basis for life. It does react to hydrofluoric acid, which like ammonia has also been suggested as an alternative to water as the solvent for life-bearing chemistries, but in our context today we are more interested in silicon using molten metals as a solvent. As an example, aluminum melts at 1220 degrees Fahrenheit or 660 degrees Celsius, and is very common, while tin melts at a mere 449 degrees Fahrenheit or 232 Celsius, and lead at 621 Fahrenheit or 328 Celsius, both common components of the solder we use on circuit boards and for that reason, plus being conductive of course. Incidentally, tin, lead, and boron are also tetravalent elements like carbon, silicon, and germanium. They are also decently common, and one reason why we have a lot of silicon in our crust is that it is low density and floats in molten metal. So we figure big rafts of the stuff commonly surface on molten worlds as they cool, leaving a crust heavy with it. And silicon can handle monstrously high temperatures. Silicone doesn't melt but will catch on fire at 840 Fahrenheit or 250 Celsius. Quartz melts at over 3000 Fahrenheit, for instance. Amusingly, that means there is a non-zero chance that silicon-based life did live here on Earth way back, and was killed off as the planet cooled or when that dwarf planet, Theia, smacked proto-Earth and blew our crust off, from which the Moon later formed, and onto which we assume a long reign of comets later fell to give us oceans. But planets start hot, and can stay that way if near their sun, and it isn't too hard to imagine silicon life on a Venus-like planet or living in the lava tubes of some volcanic or Chthonian planet. Chthonian planets are believed to have originally formed as super-Earths, gas giants, or ice giants, similar to Jupiter or Neptune in our own solar system or smaller. However, they have undergone significant atmospheric loss over time from being that close to their sun. Photoevaporation, thermal escape, or interactions with their host star strips off their atmospheres and lighter elements, much as Earth lost most of its hydrogen and basically all of its helium. So you get left with a big hot ball of metal and silicon, and probably a lot of oxygen still too. These sorts of planets are likely to be pretty common in the galaxy, and also likely high on tidal forces, which might be beneficial for life. Could they hold not just life, but complex life? Well, perhaps. We normally talk about habitability in terms of surface oceans and atmosphere. Subsurface oceans are entirely viable too. Indeed, biologists generally favor life originating deep in the oceans. The problem is the power source though, as the sun allows photosynthesis and dense biomass in ecosystems, which we assume seriously helps move evolution along to let intelligence possibly develop. Subsurface oceans on moons like Europa can probably have life, as tidal forces from Jupiter on its moons is big enough to power a modest ecosystem, but while contemplating giant alien kraken on Europa is fun, it's not very likely we'd see big critters there or complex ecologies with such a limited power pump for the ecosystem. Hence the focus on surface oceans and atmosphere in our hunt for life, along with biosignatures being easier to see astronomically if they were on the surface, of course, rather than buried down in caves or lava tubes or magma seas. However, the key is a large energy flux, and a molten planet tightly wrapped by its own sun absolutely fits that bill. The problem isn't if there is energy to run the chemistry of life in these places, but if the temperatures are too hot for any life. And the answer is no. We could absolutely design some sort of artificial life form for this, it just wouldn't be carbon-based, unless we're talking diamond and graphene types of carbon, not the classically squishy bag of water that best describes life forms on Earth. Whether or not a natural life form could develop is harder to say, as evolution has to follow a path of minimum steps that engineered life forms or freak improbabilities like Boltzmann brains do not. Heat is not the only extreme that might permit silicon life. Again, it isn't soluble to the same degree and to the same things carbon-based life is, so some acidic environment might work well for it. Extreme conditions such as high temperatures and radiation might be suitable for these life forms, expanding the possibilities for habitable exoplanets. So we're definitely seeing room for silicon life in places carbon-based creatures should fear to tread, but I think we also need to acknowledge that it has some key problems, all the way down to the basic DNA, or silicon equivalent, which we'll label sDNA. Carbon-based DNA relies on a long chain of nucleotides, with each nucleotide composed of deoxyribose, the D in DNA, and a sugar, a phosphate group, and one of 4 nitrogenous bases, adenine, thymine, cytosine, or guanine. These bases form pairs AT or CG that encode genetic information. Silicon, although again tetravalent like carbon, does not readily form the stable, intricate, and versatile molecular structures that are essential for genetic material. Silicon-silicon bonds are generally weaker than carbon-carbon bonds, and silicon compounds tend to be less stable in water, which is a crucial environment for life as we know it, and why hotter areas without water interest us. However, in speculative discussions about silicon-based life, we do have some ideas that have been proposed for silicon-based genetic-like molecules, or again, sDNA. One such concept is the use of silicones, which are silicon-oxygen compounds, to create a chain or polymer structure that could store information. Silicones are more stable in some conditions than other silicon-based compounds, but they are still quite different from carbon-based nucleotides. This is all very speculative though, and I feel obliged to emphasize that the viability of silicon-based genetic molecules remains highly speculative, and there is currently no empirical evidence to support the existence of such molecules in nature. Now we have the basic building block of life, such as these silicones, and something for them to do chemistry in, a solvent like water, or acid or molten metal. But we need energy, or more accurately, energy flux. Heat offers that, and we might see some interesting silicon life forms, such as those that were basically a big thermocouple running on geothermal energy. Maybe something like a giant silicon tree growing from deep in the molten sea to up into the empty sky above to radiate heat away and run on that flux. Or a mobile version of that might be some huge silicon whale, or kraken, or a very long Dune sandworm that ventured through the lava or the huge lava tubes left inside some slowly cooling but still viciously hot Chthonian planet. They might also run on electromagnetic radiation. Remember, silicon is our ideal semiconductor material and the basis of modern solar panels, and I think it is plausible enough to assume that photosynthesis might be no harder to evolve than some equivalent of a biological thermocouple or photovoltaic cell. This opens the door to some interesting options for life forms, as we might easily have creatures with quartz hides instead of skin, or quartz bark trees with roots that drank in magma, or were long hybrids of wire, root, or hair that were very high in thermal or electrical conductivity. You might have weird options like an organism that was a gas bag made of silicone latched onto a gas vent from a molten interior to a low pressure near vacuum airless surface above, feeding on those mineral-rich gases while soaking up sunlight from its natural photovoltaic cells. Indeed, that's the sort of scenario where life might evolve on a moon like Io, tidally racked and volcanic from Jupiter's gravity, and be able to spread out to other nearby moons or a planetary ring like Saturn. In our Avoid Ecology and Space Whales episode, we contemplated that scenario more, and options like a natural Kardashev 2 civilization or Dyson swarm of quasi-organic critters who might be no smarter than a whale or a fish or even a coral reef. It is not hard to imagine silicon-based life forms manifesting as something like a coral reef made of quartz instead of calcium carbonate, though we should not assume silicon-based life is all silicon any more than we are all carbon, and they may well swim through oceans of molten lead with skin made of iron or titanium or tungsten. On the flip side, just because silicon can survive high heat doesn't mean it's unable to handle great cold either, and I could imagine worlds where slabs of quartz among the ice ran on low energy flux but ultra efficient low temperature conductors, or a planet whose sky was dark from a thick atmosphere the sun could not penetrate, but which had storms that ravaged that planet and wrecked any carbon life, but the quartz monolith shot through with veins of metal soaked up the lightning and ran some mind upon it that danced on the hazy edge between a brain and a computer. And while it's not our topic for today, another type of silicon-based life would be robots and computer minds, and if it is the habit of alien civilizations to send out von Neumann probes to explore for them, and to conclude that colonization is harder than they wish to pursue, we might see the mutant remnants of those self-replicating probes slowly shift from being a machine with some lifelike characteristics to a life form that is based on silicon and has some machine characteristics. The possibilities seem vast, but that said, we now have plausible chemistry and various ecological niches available from various power supplies, allowing large and diverse ecosystems, and we can move to the SETI aspect of silicon life. In other words, we know where it might live, so how can we spot it and recognize it? What are some possible silicon biosignatures? These are hard to say for biosignatures, as without knowing the chemistry they use in any detail, things like waste products are hard to guess at. If it were silicon dioxide, the way carbon dioxide is a waste product of animals and modern industry, then we would not likely see that in an atmosphere, but we might see it as a waste product covering the surface of a planet as dirt covers ours, and which is very unlike natural regolith in the absence of life. We might notice a biosignature in the albedo of a planet, that it wasn't reflecting certain expected wavelengths, as those were being used for natural photovoltaics, much as plants use certain frequencies for photosynthesis. If they'd spread out over a metallic rock or into space, they would surely alter the plant's spectrum off the natural surface and its expected characteristics. It is inherent to life that it should alter the world around it and evolve so as to use more of the available energy and resources of its ecosystem, which it should also seek to expand from into new niches, and thus it is inherent to life that it should leave some signature. But if you are a vast whale skinned in quartz and titanium, swimming around the subsurface magma pockets of a planet that makes Venus look hospitable, it would be hard for us to find you. Indeed, strictly speaking, such things might dwell deep below Earth, but that would be a topic for another time too. In the end, for the topic of silicon-based life, while it shows some promise as a plausible option for life, we are left with far more questions unanswered than we would like, and can do little more than speculate for now. But as we venture deeper into the mysteries of the universe, finding new exoplanets every day, we are reminded that our own world is an enormous canvas upon which nature paints many surprises, and on which strange life thrives in the most hostile circumstances. And yet this world is but a pale blue dot compared to the cosmos, which is a near infinite canvas on which even stranger tales might be painted. The possibility of silicon-based life forms challenges us to cast aside our preconceived notions and explore the uncharted territories of existence. Whether we find these exotic organisms or not, the search for them broadens our horizons, as the horizon of this universe is very broad indeed, and doubtless it contains wonders we have yet to even dream of. This is probably a good time to be grabbing another drink and a snack, and incidentally, also a good time to grab one of our new official SFIA mugs, linked in the episode description. As a bit of channel trivia, shortly after I wrote this episode, I decided to write Crystal Aliens as something of a companion video sequel, but it felt like it might be too long as a companion and a bit too soon as a sequel, so I released Crystal Aliens as our monthly Nebula exclusive instead, and it came out on YouTube a year later in 2025, but was recorded in 2023. Our next new segment has a somewhat parallel story. I considered doing a focused episode on phosphorus-based life, but had done a deep dive about the role of phosphorus in the Fermi paradox in late 2020, and even if it was fairly different content, felt it was a little bit too soon. That episode had originally been pitched to me by my friend and longtime editor Jerry Gurn, who co-wrote it, along with the earlier episode on Void Ecology, and he'd come by my farm here in Ohio to stay and visit for a few days, and it got me primed to discuss the topic further, but I felt like he should be involved in a sequel too, and he ended up starting a new job shortly after it, so it got shelved. For those who didn't know, Everybody involved with the show besides me is a volunteer on their spare time, maybe a couple hours a month. Most are just fans who help review the occasional script or send me an outline for an episode idea they had, which usually changes a lot before becoming an episode. I shouldn't say I'm always looking for new episodes, because in spite of having done about 800 episodes to date, I still have a backlog of them waiting to be made. We only ever recover topics because I feel they need refreshed. But I always welcome new episode ideas, and I'm always looking for folks who want to help review scripts, brainstorm ideas, review draft videos, or help moderate our various online forums. And speaking of new ideas, Phosphorus Life, the builders of alien DNA. If carbon is the framework of life, then phosphorus is its architect. It builds the scaffolding of our genetic code, connects the energy packets that power every cell, and glues together the molecules that define what it means to be alive. And yet, in the vastness of the cosmos, there may be worlds where phosphorus isn't just a supporting player, it's the star. Here on Earth, phosphorus is rare but indispensable. It's the backbone of DNA and RNA, the bridge that links nucleotides into long, information-bearing chains. It's the spark in ATP, adenosine triphosphate, the molecule that stores and releases energy for nearly every biological process. And as more channel trivia, the physics of ATP was actually the topic of my thesis for grad school, around a quarter of a century ago now. That never got finished, incidentally. I ran off and joined the army during the war. Without phosphorus, our cells could not divide, our brains could not think, and our chemistry would collapse into stillness. Yet phosphorus is a quiet element, often locked away in minerals that don't dissolve easily. On many planets, it might remain trapped in rocks, never entering circulation. So if life depends on it, perhaps that dependence itself is a sign that our biochemistry evolved under improbable luck, a reminder that what works here may not work elsewhere. But it could also mean the opposite, that phosphorus, with its energy-rich bonds and versatile chemistry, might make an excellent foundation for alien life on worlds where it's more abundant or behaves differently. Phosphorus is special because it sits at a crossroads between energy and information. Each phosphorus atom can hold multiple oxygen atoms in high-energy bonds, forming compounds that act like chemical batteries. When these bonds break, they release bursts of usable energy, small enough for biochemistry but big enough to matter. It's the perfect fuel for molecular machines, which incidentally was why it was the topic of my graduate thesis. Now, imagine a world where phosphorus plays not a supporting role, but a central one, where its energy chemistry replaces carbon's structural role entirely. On such a planet, we might see phosphorus-sulfur or phosphorus-nitrogen compounds forming flexible chains, serving as both backbone and battery. These molecules would not just store energy but embody it, life whose very structure pulses with chemical potential. Imagine cells that breathe by shifting phosphorus bonds from one oxidation state to another, cycling through bursts of stored energy as if every heartbeat were a chemical thunderclap. Some scientists have even speculated about this idea indirectly, when phosphorus was detected in the upper atmosphere of Venus. For a brief, thrilling moment in 2020, astronomers thought they discovered phosphine gas, a molecule that on Earth is produced mainly by microbes. And that is what sparked Jerry and I to write the Fermi Paradox episode on phosphorus. Later studies questioned that detection, but the idea remains fascinating. Phosphine is a chemically unstable molecule, and if it really were present in Venus's clouds, something, or someone, would have to be making it continuously. Whether that something is biological or geochemical is still uncertain, but the chemistry itself is rich territory for speculation. Phosphorus could enable life on worlds like Venus, where water is scarce, but sulfuric acid and heat dominate. In such places, phosphorus might fill the same ecological niche that carbon and water do here, forming long chains, dissolving alternative solvents, and transferring energy through rapid bond shifts. Instead of DNA, alien life might encode information in phosphorus-based polymers, each bond storing not just data but energy, like a living flash drive powered by its own circuitry. We could even imagine metabolic lightning, organisms whose biochemistry is electrical, using a flow of charged phosphate ions through mineral membranes to power reactions. Phosphorus compounds can conduct electricity under the right conditions. If life evolved to control that property, then intelligence itself might have begun as chemistry, learning to spark. But phosphorus can be dangerous too. On Earth, some of its compounds are violently reactive. White phosphorus can spontaneously ignite in the air. We use it in artillery munitions, which was actually my area in the army. It burns with an eerie green glow, and the ancient Greeks called it the devil's element. If life arose from such chemistry, it might literally glow in the dark, luminescent life forms burning with fire of their own metabolism. Imagine a world half shrouded in fog, its surface carved by shallow acid lakes, rich in phosphorus minerals. Along the shores, mats of biofilm glimmer faintly green as they draw energy from oxidation, releasing phosphine back into the air. Lightning storms feed the process, recharging the atmosphere with energy for the next cycle. The biosphere becomes a planetary circuit, each cell a spark in an endless electrical web. Phosphorus is also one of those rare elements that connects the organic and the inorganic seamlessly. On Earth is the link between metabolism and geology, cycled by erosion, volcanism, and decay. That makes it a natural candidate for planets where biology and geology are intertwined, where living systems depend on constant mineral interaction. A phosphorus world might not have lush forests or oceans, but instead, slow-moving mats of bioluminescent slime stretching across mineral plains, each square meter an active part of the plant's metabolism. Would such life be intelligent? Possibly not in our sense. A recurring issue with our alternative chemistries is that in many cases it doesn't necessarily favor an energy-dense ecosystem that could support predator-prey cycles that might give rise to intelligence, which is very expensive in evolutionary and metabolic terms. Still, phosphorus is what essentially powers our cells, so it might allow more robust life if it was at the center stage. Its chemistry might be lively, dynamic, and beautifully alien. Evolution might favor organisms that act as energy relays, transmitting charge and nutrients through vast colonies like electrical coral reefs. Over time, those networks can become complex enough to behave almost intentionally, life that thinks through conductivity rather than neurons. And while phosphorus life might sound exotic, it's worth remembering it already runs through us. Every heartbeat, every thought, every breath relies on the same chemical principle, a phosphorus atom at the heart of a molecule waiting to release energy. It is, quite literally, the spark of life. So perhaps on another world, evolution built its entire system around that spark. Instead of life built on carbon's versatility, it built on phosphorus's energy. Instead of a biochemistry of flexibility, one of fire. And if one day we detect phosphine or other phosphorus compounds on an alien world, stable, abundant, and persistent, it may not be proof of life as we know it. It might be proof of life as we don't. Our next topic is going to be crystal-based life, and is a quasi-sequel to our silicon-based life topic from earlier, and one of the notions in it plays off something I said a moment ago. Intelligence is very expensive in metabolic and evolutionary terms, but that's based on our biology. One might imagine a planet rich in crystals and natural semiconductors developing intelligence for very different costs and reasons. Crystal aliens. Crystals are not alive, but mimic life in many ways, including growing. And yet, on distant alien planets, could life have grown based on crystals? We've discussed some alternative chemistries and solvents life might operate under besides carbon and water, such as ammonia or silicon, and many others have been suggested. But one popular option we see in science fiction a lot is life forms made from crystal. We had the crystalline entity from Star Trek The Next Generation that devoured Lieutenant Commander Data's homeworld, for instance, and many more examples in sci-fi. But crystalline life represents some interesting challenges and options, so I thought it would be a fun topic for our monthly Nebula exclusive. We'll explore some of the ways this might be possible, then we'll take a visit to 5 planets with 5 very different and harsh environments, and 5 very different types of crystalline ecologies: Vulcan, Ribbon World, Long Noct, Telluride, and Tempest. Now in the past, we've focused on a specific element or molecule like silicon or ammonia as a substitute for the existing structure in terrestrial life, or that existing basic solvent that chemistry takes place in, like water. Silicon replaces carbon as a scaffold that more complex organic molecules get built around because it has similar properties. Ammonia replaces water as the solvent chemistry takes place in because it's another good solvent that's also plentiful in the universe. Crystal-based life is a little more complex though because we can't just plug it into our vision of existing life. Crystals are also an incredibly broad category of materials, whose common denominator is that they form relatively simple patterns in 3 dimensions from some atoms or molecules. At the large scale, this tends to be visible as sharp angles and flat surfaces, and often a transparency to light. This orderly arrangement of atoms, molecules, or ions extends uniformly in all 3 spatial dimensions, contributing to the crystal's unique physical properties. The formation of crystals often occurs through natural processes such as the cooling of a liquid or the slow evaporation of a gas, leading to the gradual organization of particles into a repeating pattern. This process can happen in various substances including minerals, metals, and even organic compounds. Indeed, one of the best known is sugar crystals, and sugar is certainly an organic molecule. The specific pattern of a crystal lattice, which defines its symmetry and structure, is crucial in determining its physical and chemical properties. There are quite a few lattices, but the most common ones are the face-centered and body-centered cubic lattices and the hexagonal close-packed. Generally, they do represent the most tightly packed arrangement of particles you can make, and as an example, if you have a bunch of coins the same size, your tightest packing is going to be one with 6 more arranged around it in a hexagon, and expanding beyond that in the same hexagonal packing. And 91% of the area will be filled that way, but this will vary a lot if you have 2 different types of coins or what their ratio is. When we're making these from atoms or molecules, it can result in a lot of very interesting properties, some of which we would think of as either quasi-organic or plausible basis for life, and semiconductors might be a very good example of that, which we'll return to momentarily. But I should get the conversation started by saying that a crystalline life form is a broad concept. For one thing, an organism need not be entirely crystalline to qualify, given that the minority of atoms in our body are carbon. Nor should we be calling something crystalline life just for having some crystals in it, since we would then qualify too. So we want to be looking at cases where a large portion of the organism is crystalline, or where some vital feature is. This is easier for the idea of a mobile alien, as while we might imagine a big monolith of crystal on some lightning-racked planet being essentially a natural computer, using crystal for muscle and mobility is a bit harder. Not necessarily impossible though. All muscles approach motion essentially as a ratcheting system, pulling taut or relaxing to move the more rigid endoskeleton we've got. And we could have a critter with a crystalline skeleton, but it is worth noting that there are some organic crystals like naphthalene diamide that have flexibility by having stacked layers that bend or slide, and thus might allow flexible and mobile structural joints. Though again, we might simply have a creature whose skeleton was crystal, or whose hide was. Our bones are not simply rigid structures that you can just casually replace with metal pins or rods. They are involved in the production of our blood cells, which are most of our cells, as well as storing and releasing of minerals and fat. But those do not have to be included on a life form, or could be served by some other organ. Something more amoeba-like might learn to secrete crystals as a bunch of bones or exterior scales, or like crabs, go and get the discarded ones. Indeed, in Brandon Sanderson's excellent Mistborn series, there is a shape-changing species that is basically a blob that will steal discarded bones from humans, or even animals, or a mix of many of them to give themselves a skeleton, and some of the more sophisticated creatures instead have artificially crafted skeletons made from crystal. This is probably our low-hanging fruit of crystal life forms, since it's very easy to imagine a creature developing a crystal skeleton, especially given that the inorganic part of human bone mineral is already constituted of a poorly crystallized hydroxyapatite of calcium phosphate, which gives them their rigidity and strength. The real question isn't if it is possible, but if this is going to give a skeleton or protective plating better than other options available, as otherwise they might just evolve a normal skeleton of bone after a while, even if they started as crystal. This would depend a lot on the native environment though, as while crystal tends to be brittle and rigid, as we already noted there are exceptions, and moreover, a lot of substances we think of as flexible are not when in a colder environment. So too, some wouldn't even be able to exist in a hotter environment, while a crystal such as quartz or dolomite can handle temperatures that destroy normal life. It may be that a hypothetical crystal life form might fare better in an Earth-like environment than we do, but regardless, there are many environments where we could not exist and they could. high pressure ones particularly come to mind. There's also the matter of energy flux and storage, which are critical aspects of life. You can't have life, especially complex and robust life, without a lot of energy transport going on, or energy flux. The sun is our main one for Earth now, but in the past before photosynthesis, our planet's volcanic vents are thought to have served that role in a lesser capacity, though one that also allowed a nutrient-rich bath near where the energy was coming in, much as coastlines or rain on topsoil does. This could include deep subsurface oceans churned by volcanic or tidal forces, allowing even frozen moons around dimly lit gas giants to potentially host life. As we noted in ammonia-based life forms, ammonia is a solvent that's nearly as good as water in most respects, better in a few, and nearly as common in this universe as water, unlike some other possible liquids like quicksilver or molten magma, which is common enough but rough on most complex molecules. But because water is such a good solvent, it also makes life hard, meaning you need to wrap your organism in a waterproof outer layer, and means any of your energy storage either needs to be in such a protective layer or hydrophobic like fat cells are. Sugar obviously dissolves in water quite easily, so any organism producing sugar to live can't just pile up sugar crystals somewhere like we do in our artificial sugar refining processes. Sugar dissolves well in polar solvents like water, ammonia, or methanol, but does not dissolve in non-polar solvents like gasoline or diesel. Putting sugar in someone's gas tank is a well-known prank that, like cow tipping, has a lot of urban legend around it. Sugar can clog the fuel filter and cause damage, but this is from the sugar not dissolving and clogging the filter. Various alkanes like pentane, hexane, heptane, and aromatics like toluene, benzene, and xylene are not polar solvents that you could have large pockets of on some planet, and in which a life form might opt to use sugar crystal as an energy storage medium. And while you could find a lot of that in crude oil, which is the byproduct of life on Earth, we do find many of these substances occurring on seemingly lifeless worlds, particularly methane. And this is just sugar. Many crystalline substances might dissolve in other common solvents and at different rates and saturations. For me, this summons the image of a sugar monster alien roaming the subsurface gasoline seas of some icy dwarf planet like Pluto, or giant sugar ants roving the megahives of some tidally heated moons. And these are certainly intriguing options, though I would not place wagers on their likelihood. We might imagine this as a subset of life forms, sugar or candy aliens. It is easy to imagine a predator-prey cycle developing that way, or 9 out of 10 dentists recommending such planets be quarantined. However, while imagining alternative chemistries for photosynthetic life, or weaker ecosystems running on tidal or geothermal energy is interesting, crystals can be used for direct sunlight conversion into electricity. This is what solar panels are, as well as for energy storage. Lithium-ion batteries have a cathode made of a lithium cobalt oxide crystal, and we have some new ones that use lithium and sulfur. There's likely to be many that store energy less efficiently too, which might pop up naturally. That said, crystals storing energy tends to be a common theme in science fiction with a dubious connection to reality. I remember in one of the Season 1 episodes of Babylon 5, set centuries in the future, Mr. Garibaldi is trying to build a motorcycle, and his alien friend Lanier replaces the gas engine with a Minbari energy crystal. I quite enjoyed that episode when it came out when I was 13, but even then I knew enough science to wonder about that, and also wondered why no one had motorcycles in the future. Now it is something of a B-plot filler for the main story of the episode, as well as a blatant product placement for that motorcycle company, and there was also a particularly hot period for the magic power of crystals, so it's not too surprising, and we see that with the dilithium crystals of Star Trek too, or the kyber crystals used for focusing in Star Wars lightsabers. And there at least there's some scientific basis for the concept. We did and do use crystals for focusing light beams. What exactly dilithium crystals do, given that they are entirely fictional, has tended to be vague and inconsistent and full of technobabble. And this stands to reason if you're trying to imply an energy storage or generation capacity orders of magnitude beyond modern batteries or chemical fuels. We could hypothesize something weird like a given crystal lattice being good at slowing neutrinos down so they can be absorbed by normal matter and causing a small nuclear reaction as a result, but otherwise crystals wouldn't tend to be any better at storing energy than any other chemical or battery rig-up, nor do they need to be for the purpose of biological life. Though again, a lot of batteries do use thin sheets of crystal substances as layers. Alternatively, they are very good options for power generation, in that even a primitive semiconductor solar cell is more efficient than the C4 photosynthesis process, which is the most efficient of the photosynthesis processes we have. There are organic semiconductors and naturally occurring semiconductors, and it isn't too hard to imagine an organic solar cell emerging. Silicon is not the only element you can make semiconductors from. Indeed, this year is the 150th anniversary of Carl Braun discovering and documenting the first semiconductor diode effect, and that was between a simple metal point and a galena crystal, which is a mix of lead and sulfur and the main ore for lead, and one that you can smelt out in an ordinary wood fire. Maybe some simple life form might emerge on a hotter planet where metal veins and galena crystals were common and exploit that. Certainly, silicon is common enough in the universe and prone to floating up in rafts on magma, so likely always be common in planetary crusts. For us it is biologically inert, but a different chemistry might use it, and there's also nothing stopping an organism from evolving to use that inert silicon as a nice protective outer layer alternative to scales or skin. If ever an organism evolved a natural solar panel and a way to use and transport that generated electricity, which is not a big jump either when you contemplate neurons and nerves, then that's going to be one of those evolutionary avalanche events like photosynthesis or oxygen breathing that reworks the entire ecosystem as that develops and diversifies. It might allow a much higher amount of biomass and activity than even photosynthesis on Earth does too. The bigger your ecosystem and the faster it runs, the faster evolution in general is going to go, and loosely speaking, the bigger your food chains. One interesting thing though is that while photosynthesis is taking sunlight to produce sugar as a fuel you can consume then or later on, the photovoltaic effect and solar power just produce electricity, not a fuel you can burn, or rob by eating the plant and stealing its sugars, or eating the animal that ate that and stealing their fats and proteins. So if you didn't have a particularly good and efficient way to store that energy, you could end up with an ecology that was running heavily on electricity during the daytime and use that process only for limited battery storage, which isn't super efficient normally. They might not have a normal predator-prey cycle since you're not trying to eat each other for energy then, just steal nutrients, which might be concentrated in that organism or to eliminate competition for sunlight. Of course, they might evolve a decent chemical battery, they're not tricky or problematic with biology, or take advantage of something like thermal heat storage. For that matter, we could also imagine organic or crystal thermophiles evolving to generate electricity from heat, or simply electric heaters to produce heat that might then be returned as electricity, albeit at low efficiency. Let's wrap up by imagining 5 worlds on which some crystal life popped up: Vulcan, Ribbon World, Longnoct, Televide, and Tempest. On the planet Vulcan, whose bright sun began going subgiant millions of years ago, all the water slowly boiled away, leaving a hot planet with a thin and toxic atmosphere of heavier chemicals, particularly sulfur, which often cause crystal formation on the landscape below. There's no animal life bigger than an insect, but there are vast crystal structures on the hazy edge of life itself that generate energy for the ecology hiding under them. Here, as the sun rises through the chemical haze, life bursts into activity, powered by the photovoltaic crystalline structures dotting its surface, and hiding inside them and tunnels near them that remind explorers who found them of the early Martian colonies in their domes and tunnels. While the insects here are not very similar in basic biology to terrestrial bugs, they have crystal endoskeletons of a wide variety of hues and use a great deal of bioluminescence in their communications. On the Ribbon World, a tidally locked planet near its dim red dwarf sun, life evolved in those eternal twilight seas on the unmoving day-night terminator. The planet's orbit is somewhat eccentric and causes a good amount of tidal activity and thermal events in those twilight seas. In time, some life adapted to the eternal sunlight of the day side,
which varies little over time, merely by location. And as it grew ever more arid near the hot center where the sun is at constant noon, life adapted to move away from using water as much in favor of growing various crystalline structures from the abundant silicon there. While scientists believe these two types of life had a common origin in the distant past, they are very unalike. But what's interesting in the last few million years is that this dayside electric plant life has learned to be more tree-like in its existence, grown tall and with canopies to compete with neighbors for sunlight. Moisture has begun to be able to move back into these crystal forests and jungles to allow life from the twilight sea to adapt itself to live there too, under the rainbow-lit forest canopy. On the moon Longnacht, there is very little tectonic activity anymore, as it was once a large and geologically active moon, but slowly cooled and tidally locked. Life evolved earlier there, and its now thin but still present atmosphere used to be thicker and helped slow down that tidal locking. It now has long days and nights like our own moon has, but the photovoltaic life that adapted there to make use of silicon and metals to make organic solar panels and wiring also evolved natural thermal wadis to store heat for later power generation. They grow large hollow and insulative crystal balls beneath them and fill them with materials with a good thermal capacity, in which they grow roots of conductive wires and thermopiles to send electricity to turn into heat that they then reclaim as electricity by thermoelectric effect during their long nights. On the planet Telluri, there is a thick crust over magma that tends to have lots of pockets of different materials and densities, and here we have a microscopic organism that evolved to tunnel between various pockets, and at one point left a lot of bismuth telluride crystal in its wake, a common thermocouple material. No large animals ever appeared on this planet, but while these microorganisms grew and diversified, they left in their wake lots of large networks of tunnels lined with these thermocouples and other conductive metals that electricity moved along, and these developed into neural networks and even simple brains in some places, able to send signals to each other on the wider and somewhat ragged planetary grid. These are very spread out neurons, but also very high-speed ones, resulting in millions of modest brains and several thousand mountain-sized brains spread over the planetary crust that each roughly match human intellect. Over the eons, they've learned how to prod the various microbes into performing this or that simple activity for a very limited control over their environment. On the planet of Tempest, the sun never shows its face, though you can see the sky brighten or darken slightly over the course of its 12-hour day. Storms rage across the world constantly, mostly west to east, tearing up dust and mud and depositing sediment as they go, and the volcanically active world spews new volcanoes and metal ores at an impressive rate. Sometime in the past, a very complex mix of electric conductor and crystal formed that can grow as thin, lightning towers, thin as they are north to south but long from east to west and quite tall. They absorb the numerous lightning blasts and release in turn a slow, dimmer glow. Scientists aren't sure if the lightning towers are alive. They have complex natural superconductors running through them that some think might be a simple neural network, but others argue it is merely a natural way of spreading the lightning energy around. Many of these lightning towers have even developed a variety of core-like life forms on their outside, which dig in pockets and baffles in which small ecologies thrive, deriving nutrients and moisture from the mud-laden storm that passes by. In the end, it is hard to say if a life based heavily around crystals might be able to evolve naturally, but I think we've given some food for thought as to some paths it might take. And of course, whether something can evolve or not is very different than if we can engineer it. So perhaps we will find planets like Vulcan, Ribbon World, Longnacht, Telluride, and Tempest out there among the stars, with strange alien life already on them, and if not, perhaps we might create such life one day. And on that note, thanks again for joining us for our monthly exclusive here on Nebula.
Fluorine Life, the cold fire of the cosmos. Among all the elements, few inspire more respect or fear than fluorine. It is the most reactive substance in the periodic table, the hungry ghost of chemistry, forever seeking a bond it hasn't yet made. On Earth is the element that turns Teflon, into one of the slickest substances we know, and the one that makes uranium hexafluoride boil at room temperature. But in the vast theater of alien worlds, fluorine might do something far stranger. It might be the breath of life itself. On our planet, fluorine is rare and tightly bound in minerals like fluorite and apatite, where it slumbers in geological stability. Free fluorine gas cannot exist naturally here. It reacts with almost everything, even with glass and steel. Yet the same volatility could make it the oxygen of another world, the great oxidizer, the giver of fire and metabolism. Fluorine sits just above chlorine on the periodic table, one of the halogens, a group famous for its eagerness to form salts. If you were designing an alien chemistry textbook, fluorine would get its own chapter, smaller, faster, and meaner than all the rest. Its bonds release enormous energy, far more than oxygen's, meaning that life based on fluorine chemistry could thrive on worlds too cold or oxygen poor for anything like us. Where we burn sugars and oxygen, they might burn metals, silicates, or even inert gases in fluorine, a biochemistry of cold fire. Imagine a planet orbiting a dim red dwarf, its surface coated in frost that never fully melts. Temperatures hover near the boiling point of liquid nitrogen, and oxygen is almost absent. Here, fluorine could take on the role oxygen plays for us, reacting violently but efficiently even in the deep cold. In fact, at those temperatures, its fury would be tamed. Reactions that would be explosive on Earth might proceed slow enough to sustain metabolism instead of obliterating it. In such an environment, water would be as solid as granite. But hydrogen fluoride could be liquid, forming seas of pale blue acid. Hydrogen fluoride is one of the few hydrogen compounds that remains liquid far below freezing, and it's an excellent solvent, better than ammonia, even better than water in some respects. It can dissolve silicates, metals, and many organics, meaning it could host a rich chemistry of its own. In those glacial seas, fluorocarbon molecules could drift like proteins, their backbones flexible yet stable, while bubbles of gas fluorine rise from volcanic vents below, concentrating and refreshing the substance. Hydrogen fluoride as a solvent is a haunting mirror of water. It forms hydrogen bonds, though weaker ones, and its liquid range widens under pressure. That means deep under the crust of a cold planet, or inside a moon like Europa if it were richer in fluorine. You could have oceans of hydrogen fluoride where fluorocarbon life might thrive. Their membranes might not be made of lipids, but of perfluorinated chains, Teflon-like skins impervious to their own environment. A Fluorine Worlds creature would be chemical fortresses, armored against corrosion by the very element that gives them life. If we were to meet them, they would be terrifyingly toxic to us. Fluorine reacts instantly with moisture, and our water-based cells would literally ignite in their presence, even at low temperatures. To them, we'd seem like bags of explosive fuel, dripping with oxygen and hydrogen. And they might think the same of us, fragile beings who depend on a corrosive gas like oxygen to stay alive. On a fluorine world, respiration might involve inhaling pure fluorine gases or fluorides of inert elements like xenon or krypton, compounds we barely see on Earth except in laboratories. Their blood might carry metal fluorides, transporting energy as oxidation potential rather than electrons. If carbon is still present, it might exist mainly as carbon tetrafluoride, a gas stable enough to serve as atmosphere and food source alike. Imagine forests of crystalline flora, exhaling carbon tetrafluoride mist, glittering like ice but metabolizing light into fluorine bonds. And while carbon-fluorine bonds are famously strong, they are not unbreakable. Under ultraviolet light, perfluorinated compounds can photolize, splitting and recombining into complex chains. That opens the door for a kind of fluorocarbon photochemistry, a slow, cold cousin to photosynthesis. Life could harness starlight to rearrange its molecular bonds, storing energy not as sugars, but as high-energy fluorides, waiting to release that energy in controlled reactions later. To such organisms, sunlight would be less about warmth and more about pattern, a steady trickle of photons guiding an intricate molecular dance. These worlds would not be lush in the earthly sense. Their skies might shimmer pale green or violet from fluorine vapors. Their seas would fume faintly, etching any rock they met. The air would be thin but rich in potential energy, every molecule a tiny coil spring of chemical tension. And yet, within that danger could lie a slow, stable equilibrium. Ecosystems built not on gentleness but on restraint, where life survives by balancing on the knife edge between reaction and ruin. Some of the most interesting chemistries could happen at the boundary zones, where hydrogen fluoride oceans meet crusts of rich and silicates of metals. Silicon tetrafluoride gas could bubble up from volcanic vents, feeding fluorine-fixing microbes that harvest the reaction energy. Picture glowing mats of fluorosilicate biofilm crawling across the rocks, shimmering faintly as they digest stone. In time, these could form vast biogeochemical systems, coating entire continents in living enamel. And there's another twist. Fluorine, though reactive, resists radiation damage better than almost any other element. Carbon-fluorine bonds absorb ultraviolet and even X-ray energy without falling apart easily. That means fluorine life could flourish on worlds blasted by radiation. Planets close to their stars, moons exposed to magnetospheres, near black holes, white dwarfs or neutron stars, or even rogue worlds wandering through interstellar space, living off cosmic rays. These creatures might metabolize light and radiation directly, their transparent skins flickering with auroral colors as they convert photons into chemistry. So if carbon life burns warm and bright, fluorine life would burn cold and slow, living ice that feeds on starlight and stone. And if we ever find a world rich in fluorine compounds, perhaps near the galactic core, with hydrogen fluoride oceans and an atmosphere lacking oxygen, we shouldn't assume it's dead. It might just be alive in a way our chemistry could never tolerate, quietly breathing the fire we cannot survive. Next, we'll leave the corrosive seas of fluorine worlds behind and journey into the emptiness itself, to see how life might survive without any chemistry at all, in the vacuum between stars. And be warned, it's from 2019, so a bit harder to understand. All our episodes include closed caption subtitles with that in mind, and don't hesitate to use them. And now, Void Ecology.
Explorers have found life in the deepest, driest, darkest, hottest, and coldest corners of our planet. As resilient as life seems to harsh environments, maybe we might find some in space. And if not, maybe we can make some. In this episode, we're going to talk about life forms in space, specifically about evolutionary pathways that could lead to life forms that can live there. We will explore more artificial or designed life in future episodes, starting with space whales and bioships this Thursday. At first glance, life evolving in space seems implausible. We tend to think of space as a cold, lifeless vacuum, or perhaps a blazing hot, lethally irradiated, lifeless vacuum. But we've always been tentative about the lifeless part, because life has surprised us in many environments. Extraterrestrial life of even the crudest forms would confirm some important theories about how life originated, and it would create a new zeal for searching all the remote corners of our solar system for critters hiding under the ice, in rocky crags, and among the clouds. I should make a distinction right up front between life originating in a place and adapting to that place. Life can adapt to harsh environments it probably could never have formed in, and any life that might exist in space would almost certainly have started its evolution in a more protected environment and adapted to space later. Indeed, as we discussed in our look at the panspermia theory of life originating in space and coming to Earth, one might argue that planets, serving as an incubator for life, whether it originated there or not, are where it develops before emerging from those cocoons to spread across space. The panspermia theory, even if true, which it probably is not, still only suggests simple life emerged off planets and seeded them. And for today, we'll look at how simple life originating in the void might develop into something more complex and diverse. As of now, we have no evidence of life anywhere off Earth, though an assumption of its absence in this solar system is premature, because at this point we've just barely begun to explore the bodies nearest us. Mars seems like a good prospect because it has the right ingredients and most likely environment to host, or at least have hosted, primordial life, as it may have been friendlier to life in the past. But even on Mars, we've only done fairly simple biosignature tests, and only in a few spots. The Moon and Mars are the only bodies we've checked even that carefully.
While a developed civilization orbiting a distant star would leave traces we could identify from light years away, we might at best detect non-technological life around other stars by atmospheric signatures, and living things smaller than a forest are difficult to detect even from a Galileo or Cassini probe orbiting above. We might not even know if we were looking at life either. As we've said elsewhere, intelligence recognizes intelligence, but it would be very easy to mistake a patch of simple lichen absorbed from orbit that was sprawling over a continent-sized patch of ice as some type of impact dust crater or mundane geological phenomena. We also have to keep in mind, as we get further from the sun or visit worlds without thick atmospheres, that any such life is likely to be hidden below and might be quite peculiar. Science fiction's portrayals of creatures on other planets are sometimes plausible and sometimes not, but the popular visions of life that might exist elsewhere in space are generally fantastical. Space whales or leviathans are a popular trope, as they are natural extensions of the space is an ocean trope that pervades sci-fi, but I'm sure I don't need to tell most fans of this channel that a whale would fare poorly in space. Tails only work for propulsion when you're in a viscous medium like water, and the same goes for maneuvering fins. And of course, hauntingly beautiful whale songs are right out when there's no medium to carry the sound. However, if a large creature lived in orbit above a planet, there would be good reasons for it to have distinct dorsal and ventral sides. There is no up or down in space until you get near a planet. If food or threats usually came from either above or below, it would make sense for the animal's sensors to be mostly on that side. It would also be advantageous to be colored something like an inverse orca, with a dark belly that blends into the sky above and a dorsal surface colored like the surface below. But could big creatures really somehow exist in space? Certainly not by themselves. No creature can exist without an entire supporting ecosystem around them, with the exception of Boltzmann brains or arguably a hive mind. Whales can't live anywhere unless there's plankton, krill, or fish around for them to eat, and the same goes for their analogs in space. So instead of individual space creatures, we need to think about how an ecology could be established in space, a void ecology. And by the way, I'll often describe creatures by the names of their counterparts on Earth, not because I expect space creatures to look much like Earth ones, but because they would very likely occupy analogous ecological niches. In any environment that's constantly likened to an ocean, the apex predator deserves to be called a shark. But let's back up an eon or two, because life has to exist first before it can evolve into whales and sharks. Earth life probably formed in the protected environment of the oceans, where it could perform vast numbers of delicate experiments in RNA and DNA self-replication in a relatively stable temperature range and safe from ionizing radiation above. The first life forms existed exclusively in the oceans for eons before they ventured anywhere else. This is an important principle to understand, that while life can thrive in diverse environments, it does need a somewhat sheltered environment in which to form in the first place, and it needs to evolve to at least a certain extent and have certain mechanisms well established before it's ready to venture out. Probably the most life-friendly regions of space besides planetary surfaces would be the rings of a large planet like Saturn, but perhaps one closer to its sun than Saturn is. Though the geothermal energy and tidal forces near such planets might be sufficient initially, just as they likely were on Earth before we had photosynthesis. In among those rocks and ice chunks are an abundance of compounds containing the necessary elements for life. The cavities and craggy surfaces of small natural satellites also offers a fine physical environment for life, plenty of rough surface area for photosynthetic creatures to anchor themselves to, and caverns insulated from the radiation and the extremes of temperature fluctuations. The one problem life would not have in space is finding enough energy. Photosynthesis is certainly an option, as are any number of chemical processes, and we have found radiotrophic fungi in and around nuclear facilities. With the entire EM spectrum available in raw sunlight, any number of photochemical processes could be used to convert EM energy from different bands into storable chemical energy. Nor should we rule out more photovoltaic approaches, the conversion of light into electricity rather than chemical energy. The role of oxygen in Earth's history illustrates an important principle in understanding evolution. Oxygen is sometimes poorly described as a waste product, but evolution is not very tolerant of waste, so releasing O2 wouldn't have continued for very long unless it conferred some survival advantage on the organisms doing it. Oxygen is highly caustic and destructive to most organic molecules. The very first algal cells that released oxygen into their primordial ponds were probably harmed by it, but they were quickly naturally selected for their ability to tolerate it. Those that adapted to oxygen gained a major survival advantage over their neighbors, whom they had poisoned. Of course, those neighbors were also soon naturally selected for their ability to tolerate oxygen and eventually for their ability to use it. Oxygen does another neat trick that was rather convenient for the evolution of life on Earth. When diatomic O2 is exposed to UV radiation, it turns into triatomic O3, ozone, which blocks UV radiation. When enough of it is built up in the primordial atmosphere, it shielded the proto-life below, enabling it to evolve into more complex, delicate molecular forms that couldn't have withstood all the UV. Similarly, many creatures evolved to keep a layer of dead skin around them as a protective layer of armor, another example of waste being repurposed into a useful role. So we've established that primordial life needs a somewhat sheltered environment to form and incubate in before it's ready to venture out and adapt to harsher environments. Caverns inside of ice clumps in a planetary ring might be an adequate nursery for more complex life forms to emerge from, but if not, it is also possible for life to form first on planets, then migrate into space. As we discussed in our look at panspermia, it appears possible for microbe-laden rocks to be ejected into space and survive to land elsewhere. Indeed, we also discussed how it might develop on a simple icy comet. How likely they are to survive and adapt on landing on a new world depends on how well their previous environment prepared them, but if the destination is unpopulated, at the very least, they will experience no competition. Tardigrades, moss, and lichen have all been found well above the 20,000 foot or the 6 kilometer mark in the Himalayas, and bacteria and algae have been found in clouds as high as 10 miles up. It's entirely possible that under the right circumstances, and with more available biomass, those ragged fringes of our biosphere could gradually adapt to live in vacuum. Indeed, we found bacteria living on the outside of our space station. Something like this could easily happen on a dwarf planet with mountains that rise above the atmosphere. Large rocky planets tend to pull tall mountains down, but small ones can have huge mountains and thin atmospheres, both in height and pressure. A body with small oceans in which to incubate life, and mountains that life can climb to adapt to vacuum and gamma rays might be the ideal cradle for life awaiting a meteor to knock them into space. Planets can also slowly lose their atmospheres and magnetospheres, and this happens on geological timelines, potentially quite sufficient for evolution to adapt to. Nor is a meteor impact the only way for microbes to reach orbit from the surface. Many planets and moons have volcanoes or cryovolcanoes that eject material into orbit. Indeed, it's quite probable that on small double dwarf planets like Pluto and Charon, that matter is regularly exchanged this way. And more volcanic moons like Jupiter's Io might easily spread matter to their sibling moons and rings. And that brings us back to our most likely habitat for life in space, the rings of a planet. Once a variety of microbes are established there and thriving on the available ammonia and organics, they can form an ecology and evolve into all of the ecological niches. And the great thing about space is that if your species is not genetically diverse, the radiation will make you so. Wherever some creature is creating chemical energy from sunlight, some other creature is going to evolve to just take that chemical energy instead of creating its own, and the predator-prey evolutionary race is on. So if some microbes evolved to live in space, like lichen or moss, there's an ecological niche available for something that eats them, and advantage to that creature if it is mobile and can handle travel in a vacuum. Same for the spores of that space moss. Same too, we might see fairly sophisticated coral emerge, as it's quite easy to encapsulate and reshape even entire asteroids and icebergs when there's little gravity or typical erosion forces constraining you. One might even imagine them slowly hollowing such places out and expanding them like big balloons for more sunlight, and perhaps creating pockets of gases or liquids inside such reef structures, or even entire pressurized bubbles, spawning a new interior ecology. One other reason planetary rings might be the preferred environment rather than larger belts around a star like the Kuiper belt or the asteroid belt is their density. Planetary rings have shepherd moons that capture escaping material and bounce or fling it back inward, keeping the rings dense with raw material and habitats. Distance is less relevant in space, with no water or air requiring constant effort to push against when traveling, but hardly something we can ignore either, and in such rings the closest objects are separated by mere kilometers, not many thousands of them. So you could have creatures not only spread out, but even migrate to graze new areas. It's also important that the dense collection of orbiting bodies offers an archipelago of habitats that are somewhat isolated from one another, but reachable with some luck and effort. Collisions between ring objects will knock pieces off and create opportunities for creatures that have evolved successfully to migrate all around the ring, something akin to rapid continental drift. Cycles of isolation and contact are important for evolution because they drive diversity and adaptability. In times of isolation, distinct evolutionary paths are explored separately to be tested against each other later in times of mixing and contact. Waiting for the rock you're on to get bumped by another is obviously not the only way to get around space. There's no classic wind or sea currents in space, but you can still release spores, although you'll need to give them a push to set them adrift, or provide them some means of locomotion. And it won't only be spores drifting about in hopes of finding a fertile new home. Chances are, any creatures living in space will need to be able to endure long periods of scarcity, and the best survival strategy for that is dormancy or migration. On Earth, lungfish survive summer droughts by estivating, which is basically hibernating but in the summer. A creature who has exhausted his food on one rock might find that his best bet is to jump off into the void and go to sleep until colliding with a new habitat. Hibernation is always a high-risk survival path, a last resort, and migration is better, but one must begin with baby steps even where migration is possible. And one big difference from Earth, in space, one is likely to go dormant while migrating. So some creatures will simply gather solar energy and become active only when they encounter a wisp of methane or ammonia or detritus to consume, then go back to their semi-dormancy until they encounter the next. At this point, they've essentially evolved into space plankton, albeit in an ocean less nutrient-dense than Earth's. With all these spores, eggs, plankton, and sleepers drifting around, our space ecology has a well-established bottom level, and there are wide-open evolutionary niches for herbivores, insectivores, small predators, bigger predators, and yes, majestic leviathans that drift gracefully about, capturing krill and plankton. There are advantages for size and for storing materials for the journey. More size means thicker skin for shielding via the square cube law, same as we discussed for spaceship armor. Used up resources might be expelled as gas or solids to provide propulsion. For the sake of good taste, we won't explore the delta V available from strategic use of bodily waste, but it's not minimal, especially in the context of a planetary ring environment. Moreover, a thick skin need not always be massed together. One might imagine an organism developing quite large wings or fins to approximate solar or magnetic sails, which can be folded to protect against radiation as well. This also offers energy and propulsion without losing matter, which is important as there's plenty of energy to be collected while floating in space. It's only matter that is scarce. We might also imagine that it might develop some internal equivalent of a weak ion drive. One might imagine methane and oxygen-based biorockets as well, but it's critical to remember that high thrust won't be very important unless dealing with a moon or asteroid with an escape velocity of at least hundreds of meters a second, which, while small compared to Earth's gravity well, is something you'd find on only the few hundred most massive objects in a solar system, not the millions of smaller bodies. Of course, you're quite likely to encounter such bodies and be dragged down onto them, which is a nice place to get stranded at least. You might also find organisms that dwelt in orbit of such places, waiting for other life to drift in and be captured by the gravity well, or an organism that entirely takes over a large rock, like a big space crab, waiting for things to fall down onto it. But if you're a rock-clinging creature who happens to get stranded on the surface of a big space crab or whale, you might find that's a life worth adapting to, living in a place that predators steer clear of, always near a food source. Our space leviathans might soon find themselves covered in barnacles, moss, and remoras, and that they've quite unwillingly become mini ecosystems themselves. There too, we mentioned coal earlier, and them developing colonies over an entire rock and even turning it into something like a big balloon body. And this too might be an avenue for a space whale. Those space whales might interact with weak but significant gravity wells, those with several meters per second of escape velocity, by lowering down a tentacle or long tongue. Saves it delta V or damage by lithobraking, which is to say, crashing into the object to slow down. So our space whale, which we noted might have huge thin sails for wings rather than fins, might also look more like a giant space squid. Indeed, these things could conceivably get big enough to have their own noticeable gravity well, especially ones that evolved into a niche for expanding out beyond those planetary rings and moons, either down to a planet or off to distant Trojan asteroids of that planet. As the whale's shape is meant more for buoyancy, such space leviathans might start skimming gas giants and evolve to more of that big balloon whale-like shape, complete with fins, or maybe one that didn't live in the upper atmospheres of gas giants, but just dove down to grab gases. Neat notion, but before we get too carried away imagining designs for a bioship, we need to remember some things about how natural selection works and how it develops solutions to problems. We often speak figuratively about evolution developing certain adaptations for a certain purpose, but it really doesn't work like an industrial design process. The evolution of the car or airplane is a textbook example of intelligent design, not natural selection. Natural selection is a process by which small changes incrementally either improve or diminish a creature's ability to survive and reproduce. There are no other goals or purposes. Every incremental change needs to bring about a survival advantage for that generation. So while we can picture how to make a rocket, fuel, and oxidizer organically, in nature, those parts have to come about in an unplanned way, each of them having enhanced the creature's survival in some way before they came together as full-fledged rocket or solar sails or magnetic sails. And while it is plausible to chart a pathway for storing gas and expelling it as a weak rocket, or developing small thin protrusions initially to allow change of attitude, then to grow to act as solar sail wings, we can't just assume some space leviathan is going to evolve a high power source like a fusion drive that would let us contemplate using such a creature as a genuine spaceship. But here we can start bringing intelligent design into things, because while we can imagine life possibly evolving along these lines, indeed maybe even to enormous complexity, diversity, and size, what we can do with intentional design, via genetic engineering or blurring the lines between the biological and machine, alters things enormously. We will be exploring this idea this summer, and we will begin this Thursday with a look at space whales and bioships. and we'll begin seeing just what amazing options we have for void ecology once we bring technology into play and blur the lines between life and machine. But while such a thing occurring naturally would seem fairly improbable, maybe it's not too improbable, and the universe is a big place, so perhaps somewhere there is a large and diverse natural void ecology. While I generally write the episodes here and others help edit them, sometimes an episode is also co-written by one of our editors, and today's episode and our follow-up on Thursday were co-written by Jerry Gurn. And of course I wanted to thank him for that, but I also wanted to mention that he's recently released an anthology, Purple Dreams, a collection of sci-fi and fantasy short stories, one of which is about the ecology of the void. And I talked him into recording that, and it's up on his new YouTube channel if you'd like to give that a listen. You can also read a short story about the topic of Thursday's episode, The Perilous Lives of Bioships, in the free preview window of his Amazon page. You'll find both of those linked in the video description.
If you made it through that episode, I'd highly recommend the original companion episode, Space Whales and Bioships. Space whales is a bit of an old joke around here, both from the normal sci-fi context and from the whale guns rather than railgun slip from even earlier days when the impediment was even worse. Those both date from when the show was already in its 5th year. The meme is even older, and when we brought back channel merchandise a few months ago, I did add that one onto the coffee mug designs at the encouragement of my wife Sarah, just to make sure I plug those mugs again. Our Cosmic Megafauna episode from a year back also continues on some of those ideas in space whales, but neither was included here because I felt they were getting more into environmental conditions and less into alternate chemistries or core building blocks of life, which is arguably the case for void ecology too, but that's so foundationally different that I felt it deserved its own episode. Also not in our collection today is our original first alien life speculation video, Life on Pluto, which is episode 5 of the show from way back in 2015, and the first time I ever wrote an episode with the idea of doing another in mind. I don't really recommend it except for nostalgia purposes, but it's interesting to see how things have evolved over the years. Our last episode for today heads the other direction and came out just a few months ago on my 45th birthday, and actually borrows from 2 unpublished episodes, one being the original draft from Colonizing Titan, or one of them anyway, it had around a dozen versions as I recall, and 2 being a draft from Colonizing Uranus, a planet whose name I always intentionally mispronounce, and which folks have been calling for an episode on for 7 to 8 years now, and much like requests for the episode Sexy Aliens, it might get its chance some April Fool's Day, but it's important not to be breaking up laughing while narrating a script, and that's a lot harder to manage on camera, so it might be a while. In the meantime, please enjoy our most recent alien chemistry episode, Life on Methane Oceans. We always imagined life needing water, but the universe may have stocked its oceans with methane instead, and filled them with creatures beyond our strangest dreams. In our recent episode on colonizing rogue planets, we explored how civilizations might build homes on worlds cast adrift in the dark. That got me thinking more broadly about ecosystems that exist without sunlight, leading to an episode on dark biospheres, where we looked at a variety of exotic habitats. Among those, we touched on the intriguing possibility of life lurking beneath the icy crusts of moons orbiting giant planets. I also noted there that while ammonia tends to be a top-tier candidate for alternative biochemistries or solvents, methane and other hydrocarbons also have a lot going for them. It also made me think of Titan, the only moon we know of with an actual atmosphere, and thus where surface life using sunlight might be possible. While we typically associate methane with dark, frigid places, like Titan's hydrocarbon lakes, there's no rule saying you wouldn't pair methane chemistry with a bit of sunlight, crafting alien biospheres every bit as rich and varied as Earth's. And so today, I thought methane deserved its very own spotlight. We'll explore what life might look like on worlds with methane oceans, whether complex ecosystems could evolve there, and what such discoveries would teach us about the breadth of nature's imagination. So, grab a drink and a snack, hit those like, subscribe, and notification buttons, and let's dive into the methane seas to see if they could hold life. Titan and methane oceans, the basics. When we talk about methane worlds, the poster child is always Titan, Saturn's largest moon. Roughly half again as large as Earth's own moon, Titan boasts a thick, nitrogen-rich atmosphere suffused with methane, so dense you would need a pressure suit to walk on the surface. Indeed, the pressure is about half again that of Earth's, and more interestingly, the air density is about 4 times higher. Nor is it around room temperature. You would need an oxygen mask and a very heavy coat, since the temperature hovers around minus 180 degrees Celsius. For specifics, that's 93 Kelvin or negative 292 Fahrenheit, surface pressure 1.45 atmospheres, and a density of 5.3 kilograms per cubic meter. Now, like Earth, most of that is diatomic nitrogen, and even more so, it runs somewhere around 95 to 98% nitrogen. It varies by season, with most of the remainder being methane, a smidge of diatomic hydrogen, and trace amounts of ethane, diacetylene, acetylene, propane, and hydrogen cyanide. So again, not a place you want to breathe in, and even an insulated dome filled with oxygen could be worrisome since so many of those are unhealthy or flammable substances. As we discussed in colonizing Titan way back, it has a lot of interesting resources that tempt us to settle it, but if we were settling the surface in a big way, it would likely be with post-biological life. Giant server farms enjoying the ultra-core the environment permits. That thick nitrogen atmosphere might be very useful for terraforming Mars or filling space habitats, as nitrogen is rather rare in the inner solar system, and besides Earth, the only other big source is Venus, which has nearly as big a gravity well as Earth and enjoys other difficulties when it comes to extracting resources from it. But Titan is remarkable for another reason. It's the only other place in the solar system besides Earth known to have stable liquids on its surface. Only instead of water, its rivers, lakes, and seas are filled with liquid methane and ethane. Methane even rains from orange clouds, carving landscapes eerily similar to those on our own world. It's a strange mirror of Earth, a place where methane plays the role water does here, flowing in vast networks of channels and pooling in broad seas like the Kraken Mare, which is larger than the Caspian Sea. From orbit, it almost looks familiar, until you remember you're gazing upon a realm where liquid hydrocarbons dominate the hydrological cycle. And Titan may not be unique. As we catalog thousands of exoplanets, we're finding hints that methane-rich atmospheres and frigid conditions might be common, especially around smaller, cooler stars or in the outer reaches of planetary systems. Some of these worlds could be super Titans, with even deeper seas of liquid methane. There may be a lot of cool worlds and exomoons out there where life could potentially emerge. So today, we'll dive into the alien chemistry of such places, pondering whether life could not only exist, but perhaps flourish in ways as rich and complicated as Earth's jungles or coral reefs. Could methane oceans cradle ecosystems with their own predators and prey, or even spark intelligences gazing up their hazy skies, dreaming of more? Chemistry of life, beyond water. When we imagine life elsewhere in the universe, we tend to assume it needs water. That's perfectly understandable. On Earth, water is everywhere life is. It's the solvent that carries nutrients, facilitates countless chemical reactions, and stabilizes large, complex molecules like DNA and proteins. Water is remarkably good at this because of its polarity and the way it forms hydrogen bonds, allowing it to dissolve a vast range of substances. It also stays liquid over a generous temperature range, from 0 to 100 degrees Celsius at standard pressure, which is quite friendly for chemistry. Generally speaking, you can only have liquids if you have pressure. It's the nature of matter. It would tend to clump together and be held together by normal intermolecular forces, but if you heat it up, that internal motion and vibration eventually breaks those bonds, scattering individual molecules out as a gas. Keep heating it up, and eventually those molecules break. Those individual atoms start ionizing and become lone nuclei stripped of their electrons. But at temperatures that turn a solid into a gas, in a vacuum, what we call sublimation, having a bunch of other matter near it shoves those molecules back at ambient pressure, resulting in that in-between state of liquid. The higher the pressure, the higher the temperature range so that it can exist as a liquid. That's why if you put water under pressure, like we do in steam engines and turbines, you can raise that boiling point. If you reduce that pressure, you can get water to boil at room temperature. Conveniently, water is a liquid at the temperature range and pressure range that makes a lot of chemistry possible in it, as for instance it wouldn't be very handy to have a solvent that was only a liquid at temperatures that destroyed sugars and starches. It's also incredibly common, as oxygen is the most abundant element after hydrogen and helium, and hydrogen and oxygen make water. There are often issues with chemistry at higher temperatures or pressures, so do not assume a planet with a much higher surface pressure than Earth can have life at higher than normal boiling point. But water isn't the only solvent in the cosmic pantry. We've already noted ammonia as a good one. We have a whole episode discussing that, and it is made of hydrogen and nitrogen, another common element, but is liquid at sub-zero temperatures. Ammonia has a boiling point of -33.34 Celsius, -28.01 Fahrenheit, and 239.81 Kelvin, and a melting point of -77.73 Celsius, -107.91 Fahrenheit, 195.42 Kelvin. But water and ammonia are not the only common hydrogen-bonding simple molecules. Carbon, another ultra-abundant element, forms with hydrogen to make methane and other hydrocarbons. Methane has a boiling point of -161.5 Celsius, -258.7 Fahrenheit, 111.6 Kelvin, and a melting point of 182.5 Celsius, -296.5 Fahrenheit, or 90.6 Kelvin. At Titan's frigid temperatures, methane is liquid, abundant, stable, and behaves a bit like water does here. It rains from the sky, flows in rivers, and carves channels. It's hard not to wonder, could methane serve the same biological role? Since we are talking some chemistry in this section, let's explain what a hydrocarbon is really quick. A hydrocarbon is an organic compound made entirely of two elements, hydrogen and carbon, as the name implies. When you burn these with oxygen like we do with natural gas, propane, gasoline, and diesel, you usually get carbon dioxide and water as main byproducts. These molecules form the backbone of most organic chemistry, so probably bear discussion. Simple chain hydrocarbons begin with methane, 1 carbon and 4 hydrogen atoms, and we can keep adding another carbon atom and 2 branching hydrogen atoms to make bigger hydrocarbons. Big ones are basically a millipede with a line of carbon for a body, and a hydrogen on each carbon atom's side for a leg, and one at the front and back as head and tail. Methane is 1 carbon, 4 hydrogen, ethane 2 carbon, 6 hydrogen, propane 3 carbon, 8 hydrogen, butane is 4 carbon, 10 hydrogen, and when we get up to octane, 8 carbon, 8 times 2 plus 2 hydrogen, or 18 hydrogen, and that keeps going. We also have branched structures, or even complex rings like benzene, which is an inner hexagon of 6 carbon atoms, each with the hydrogen branching outward from them to form a second hexagon, or cyclohexane, which is similar but has a pair of hydrogen atoms sticking off each carbon atom. These hydrocarbons, along with water, form the basis of life here on Earth, and water's main role is as a solvent. Thus, we could imagine liquid methane serving that alternative role at lower temperatures. Sounds good, but there are serious challenges. Methane is non-polar, meaning it doesn't dissolve ionic compounds or facilitate charged reactions the way water does. Chemical reactions in such a solvent would be sluggish, partly because of the cold. At Titan's -100 degrees Celsius, reaction rates are orders of magnitude slower than at Earth's temperate oceans. Life might still emerge, but would do so on a much longer clock. Mind you, a bigger planet might have much thicker atmosphere, and at 5 atmospheres of pressure, you can get liquid methane at -128 Celsius, -112 at 10 atmospheres. That's still ultra-cold, and those higher pressures might bring other problems to life, but the combination might help to make that life a bit less sluggish and quicker to form and evolve. Still rather difficult, and as is often the case when we look at alternate chemistries for life, we start seeing why when we talk about the Fermi paradox, we often tend to assume, especially for looking for alien technosensors, that life, or at least very complex life, tends to come from water worlds. Yet methane brings intriguing possibilities. Laboratory models have suggested that the azotosomes, membrane-like structures made from nitrogen-rich organic molecules, could form in liquid methane, much the way lipid bilayers form in water. These could theoretically act as cell walls for methane-based life. Cell walls are vital to any nascent life, as is what lets you make different chemical solutions than the ambient solvent around you and keeps you from dispersing into it. And while we often pair methane with dark, cold places, it doesn't have to be that way. Ignoring that methane is perfectly common on Earth and highly involved in our own water-centric chemistry, especially as a building block for hydrocarbons, it's got options. Again, a world just a bit warmer than Titan, orbiting closer to its star, might still keep methane oceans under high atmospheric pressures. There, photochemistry could play a role akin to photosynthesis, harvesting starlight to drive the slow machinery of alien metabolisms. Even on Titan itself, energy might come from tidal stresses as the moon flexes under Saturn's gravity, sparking chemical disequilibria that primitive life could exploit. Alternatively, occasional impacts or cryovolcanic eruptions could inject heat and new materials, sustaining local hotspots of chemistry. All told, while methane isn't as versatile as water, it is abundant, it has a low freezing point, and it can still form a medium where carbon-based molecules could drift, collide, and perhaps assemble into something more. It paints a vision of life evolving at a glacial pace, in seas so cold they'd flash freeze our cells, yet still finding a way, slow, patient, and utterly alien. Could life evolve there? So, could life truly evolve in these alien seas of methane, or would they simply remain sterile pools, forever churning under orange skies with nothing more complicated than drifting hydrocarbons? In many ways, evolution on a methane world would play by the same fundamental rules it does here on Earth. Chemistry would still favor complexity in places where energy flows, where there are gradients to exploit, and where molecules can bump into each other often enough to try out new combinations. The key difference is the temperature. Colder temperatures slow everything down, from reaction rates to the metabolic churn inside a hypothetical organism. That doesn't necessarily preclude life, it just means that we might be looking at a biosphere evolving on a geological clock, where what might take millions of years on Earth could take hundreds of millions or even billions on Titan-like worlds. Evolution would proceed, but in a kind of slow motion, with each new innovation unfolding over epochs. Conveniently, the universe is a lot older than Earth. As we discussed in other episodes, while rocky, heavy element abundant planets are more common now than in the past, we could probably have some even 10 billion years back. Moreover, low density and lower gravity icy planets open the door to cryovolcanoes, moving materials back to the surface from potentially deeper down than on Earth, so such worlds might have been life possible long before Earth was. Energy is always the limiting factor. On Earth, most life ultimately draws power from the sun, with photosynthesis capturing photons and building up sugars to feed everything else. Even in our darkest oceans, deep-sea creatures rely on nutrients trickling down from above, or on chemosynthetic microbes feeding on chemical gradients around hydrothermal vents. Could methane worlds offer similar footholds? Possibly. Titan's surface might be only dimly lit by the distant sun, but there's still light, enough in theory for some sluggish form of photochemistry. Alternatively, life there might latch on to tidal flexing, as Titan is constantly squeezed and stretched by Saturn's immense gravity, generating internal heat and driving pockets of chemical disequilibrium. Or it could rely on slow, steady release of energy from cosmic rays or impacts, or localized heating from cryovolcanic activity. Those closer to the galactic core or inside old red globular clusters might get more ambient radiation. Moreover, a planet with higher gravity than Titan could maintain a higher pressure atmosphere and liquid methane as close as half Titan's distance from the Sun, and that is plenty enough sunlight for even terrestrial plants to grow off of, especially the ones that are adapted for shade. So if they can get a photosynthetic biology in place, they have all the energy they need. Their real limitation is on expending it without overheating that methane. Perhaps they develop powerful radiators to help stay cool while their metabolism functioned, as we have. Amusingly, much as oxygen, once a poisonous waste product of primordial life on Earth, eventually became critical to life functioning, I could imagine an environment like this adapting life forms that ran on ammonia or water solvents and had thick insulating hides to let them use sunlight and function quicker and more energetically. Of course, this would only be plausible if you had bigger life forms. So the bigger question is whether such worlds could go beyond simple microbe analogies. Could methane oceans spawn their own equivalent of predators and prey, of grazers and hunters, of ecosystems cycling nutrients and energy in intricate webs? It's tempting to think so. Once evolution gets rolling, complexity tends to pile up wherever there's competition. The harsh, cold environment would favor adaptations very different from anything we know. Life there might move slowly, perhaps only stirring to feed or reproduce once every few Titan days, which last over 16 Earth days each. Still, in the grand sweep of time, even glacier-paced metabolisms could branch out into startling diversity. Given enough eons, perhaps even intelligence might stir beneath those methane waves. Creatures with chemistry alien to ours, pondering their own mysteries under salmon skies. Imagining alien ecosystems. Let's go ahead and let our imaginations off the leash for a moment. Suppose life does take hold in these methane oceans. What might such an alien ecosystem actually look like? It may float. Titan's atmosphere is mostly nitrogen, but it's abundant in hydrogen, as methane and hydrocarbons, but also as diatomic hydrogen, which is vastly lighter than nitrogen, and this can be used as a lifting gas just on Earth. But buoyant life forms floating in the air has some advantage in a thicker atmosphere or lower gravity, and both would be true here. Indeed, their internal heating from metabolic processes might help with that buoyancy, much as hot air balloons function. How about in the methane seas, though? Picture vast glassy seas of liquid methane stretching to the horizon under a hazy copper sky. Instead of blue waves catching sunlight, you'd see dark, oily ripples gleaming under a distant pale sun, or perhaps on the ghostly glow of Saturn's rings if it was still on Titan. The atmosphere would be thick and syrupy compared to Earth's, carrying organic smog that filters the light into deep ambers and burnt oranges. Near the surface, we might find drifting mats of simple hydrocarbon life, the methane world equivalent of plankton. Tiny cells or vesicles, built from acetosome-like membranes, could float just below the surface, absorbing stray photons or feasting on chemical gradients stirred up by winds and tides. Maybe these microscopic drifters glow faintly with bioluminescence, signaling to each other in pulses of green or violet across the gloom. Go deeper, and life might take on more substantial forms. Slow, lumbering swimmers could prowl the twilight layers of the ocean, their metabolism so sluggish that a feeding frenzy might unfold over hours or days. With such limited energy, motion itself would be precious. Predators, if they existed, might spend most of their lives dormant, waking only when chemical signals suggest prey is near. Imagine massive filter feeders trailing tendrils through the dark methane, sifting for nutrient-rich organics, or serpentine grazers inching across the seafloor, scraping up clumps of more sessile life, perhaps anchored colonies that pull vital molecules from the current. And of course, no alien ecosystem speculation is complete without a touch of eerie light. In an environment starved of warmth and sunlight, bioluminescence could become a dominant strategy. Creatures might pulse with slow, haunting glows, either to lure prey, warn off rivals, or communicate across the murk. Entire mating rituals could be built on dazzling rhythmic light shows rippling through the methane gloom. Could such worlds produce intelligence? It's hard to say. Energy is scarce, reaction times are long, and environments like these might favor patience over curiosity. Yet life is endlessly inventive. If evolution stumbled on a way to process thoughts slowly, to pass down knowledge chemically rather than electrically, or to build long-lived, methodical cultures, there's no fundamental reason why even the frigid methane seas could not someday give rise to minds pondering the same cosmic mysteries we do. Challenges to habitability. Of course, there are plenty of reasons to doubt these methane oceans teem with life. Titan's surface is a harsh, punishing place. Methane is stable there only because it's so cold, but even slight shifts in temperature or atmospheric pressure could freeze those seas solid or let them evaporate into the haze. Over millions of years, Titan's own methane is expected to dwindle without some internal process replenishing it. Then there's radiation. While Titan's thick atmosphere shields the surface from most of Saturn's charged particles, it lacks a strong magnetic field of its own. Life on Earth is helped immensely by our magnetic bubble, deflecting cosmic rays and solar winds. Methane-based life might need to rely on sheer distance from its star or on chemical resilience we can only guess at. Given that it also needs to be rather cold, that's not quite as big an issue, but this is definitely a Jovian to Saturnine level of lighting. Even a planet decently bigger than Earth is likely to have enough geothermal heat on its own to keep methane liquid rather than frozen, so we are talking about moons orbiting planets with tidal heating, probably with anemic magnetospheres of their own, or planets close enough to their sun to be getting a decent high flux of solar wind, which risks stripping atmospheric hydrogen. Ultraviolet light is also brutal on methane, causing it to break up, which can let it reform into other bigger hydrocarbons, which is good, but also makes hydrocarbons in it vulnerable to atmospheric loss. As an upside, it's also quite likely there are many more planets outside the classic liquid water habitable zones than in them, or in the hotter inner zones, especially since the majority of stars are red and orange dwarfs, which are not that much less massive than our own sun, and thus can hoard planets nearly as easily, but which have far smaller habitable zones because they produce way less light. For instance, a star with 14% of our sun's mass would produce only about 1% as much light and have a habitable zone just 10% as wide as ours. It would also produce a spectrum much heavier on infrared and much lower on ultraviolet. Implications for the search for life. Still, even if life is unlikely on Titan itself, such worlds expand our sense of where to look. Methane-rich planets and moons might be common across the galaxy, especially orbiting cool stars where ice giants and their moons can form easily. That means if life can arise in methane oceans, the universe might be teeming with ecosystems utterly different from ours. Probably simpler ones where no technocentra will emerge, but life, by definition, alters its environment to live, and thus produces biocenters which we might spot in the atmosphere and the spectrum it absorbs, reflects, and emits. So, what would we look for? Subtle shifts in atmospheric composition, seasonal changes in haze, or chemical imbalances that hint at metabolism. These are the signatures we'll seek with future telescopes. Close to home, one day we might drop submersibles in Titan's sea to taste the hydrocarbons directly, hunting for even the faintest whiff of alien biochemistry. In the end, Methane Worlds remind us just how parochial all thinking can be. We look for water, for Earth-like temperatures and pressures, because that's what we know. But nature may be far more adventurous. If life can write its story in methane, crawling or drifting through seas cool enough to crack steel, then how many chapters of biology are we missing, simply because we didn't think to turn the page? So let's keep wondering, keep searching, and keep expanding our idea of what's possible. After all, the universe has a way of surprising us, and I suspect it still holds more alien oceans and stranger forms of life than we have ever dreamed. Closing thoughts. So there we go, and for the record, this is not the longest episode of SFIA. We've got at least 2 compendiums that run longer, and neither of those include order episodes or scripts either. Whether we'll do more of these anthology-style episodes in the future, I'm not sure. I generally disapprove of compilations. After all, that's what playlists are for, or were for. But I was reminded that not everyone watching or listening finds us on YouTube, and I've been terrible at keeping playlists updated anyway. Also, I gather YouTube doesn't recommend them as much anymore either. Plus, with over 800 episodes now, most folks have not seen most of them, and bringing a few of them together alongside new material seemed like a good way to explore a topic in full while still adding something fresh, and setting the stage for some more episodes on the topic. As a reminder, if you'd like to help pick which of these biochemistries we'll explore next in a full-length deep dive, we've got a poll running over on the Community tab. When we talk about life in the universe, we tend to imagine creatures a lot like us, carbon-based, water-loving, and oxygen-breathing. But one of the biggest lessons from science is the universe does not cater to our expectations. Life could be born from acid or ice or flame. It could breathe fluorine, swim in ammonia, or grow as crystals beneath a frozen sea. It might think slower than glaciers or faster than lightning, live for seconds or for eons, and still count as life just as much as we do. We've seen today that the building blocks of life are flexible things. They can be reassembled from elements that are rare here but common elsewhere, adapted to plants that would kill us instantly, but might be paradise to something else. The lesson, as always, isn't just about aliens. It's about imagination. Nature doesn't run out of ideas, and neither should we. Even if we don't find these strange alien chemistries in nature, it might be that we might be able to engineer them to bring life to strange new worlds that wouldn't be ideal for us in terrestrial life forms. And maybe that's the real point of exploring all these strange chemistries, not just to wonder what's out there, but to remind ourselves the possibilities are endless, that every time we think we define life too narrowly, the universe whispers back, "You haven't seen anything yet," and a challenge perhaps to fill in the blank where it hasn't. So, whether the next great discovery comes from a telescope, a test tube, or a world orbiting a red sun, I have a feeling it will surprise us, and I wouldn't have it any other way. As always, this is Isaac, author of SFIA. Thanks for watching, and we'll see you Thursday. Until then, have a great week.